and providing deterministic and latency optimized characteristic. This is a very important aspect that FPGAs with their spatial architecture provide. And of course, tightly coupling with transceivers and multi-mode connections. And that is really a key, that in order to provide a full solution in a system, you need to go beyond the performance of 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 traditional solutions. So the tremendous opportunities of combining AI requirements with the AM capabilities. But as we say here in the United States, there's no free lunch. AI compute requirements is, according to many sources, doubling every 3.5 months. And so as models become more complex, the data, the model complexity grows exponentially. 7,000x in 5 years. That is really a tremendous amount of complexity. And how do we deal with that? So we need to find, as researchers, solutions for that are practical. So that is a very big challenges to computing, to conventional computing platforms. So we have to look for new ways of addressing this. But before going that, let me talk about how to improve the FPGA design process, because as you know, FPGAs are very efficient, but very hard to program. People say, and you all know that it's far more difficult to program an FPGA than it is a CPU. And here you see where you have a trade-off between something that is very efficient, like a dedicated ASIC, and something that is very flexible and easy to use, like a CPU. And so the question is, can we keep FPGAs easier to program while making them easier to use? That is really the question. And here, I'm not going to go into a lot of details here, but I just want to give you a sense of how we look at these processor style software and firmware layers of abstraction. At the very top on the left hand side, you see the top layer of abstraction, where you have software, applications, algorithms, languages, machine codes, and that is built on top of what we call a software hardware contract. That is an instruction set architecture, an ISA, an ISA, and that is on top of hardware. That it relies on microarchitectures, gates, registers, devices, transistors, physics, etc. Using that model of the level of abstraction, you could see a CPU in the middle where it uses, languages like Python, C++, and compilers based on architectures like Intel, x86, ARM, that are on top of hardware, the CPU microarchitecture, what makes the ISA work. And GPUs use the same level of abstraction. So in this way, any software can run on any hardware as long as they abide by this same ISA contract, the software and hardware contract. And that makes these applications usable across domains. There is a way to do this with FPGAs by implementing soft FPGA processors, which we call overlays. Now, overlays have been around for a very, very long time. The key here is that we have now technologies that will allow us to use the same level of abstractions in order to implement the same domain-specific architectures using CPUs, so that we can provide the same programming experience as a CPU using an ISA that allows hardware and software use, looking at FPGAs as programmable processors, and adopting a myriad of processor architectures, whether it be vector, domain-specific, etc. So this soft FPGA can really be the specialized domain solution, and I will be explaining that in the next few slides. Here you have on the left-hand side your traditional hardware flow, where you have your application on the left-hand side that runs on some RTL that is downloaded to an FPGA through an EDA tool like Quartus, generating bit streams. That is the traditional way of working with FPGA hardware. The way to work with overlays is that you have overlay specialized developers, like researchers like you, that develop these very specific domain-specific requirements, create a hardware-software contract, build overlay software tools on the center, and that provide a hardware overlay development. That is the traditional flow. And on the right-hand side, you create your bit streams that implements a domain-specific architecture once. You implement that bit stream just once. And so it saves you from continuous to to place and route and compile, and instead use a software compiler toolchain to execute basically binaries. And that binaries is what makes the difference in this very fast development flow. So the overlay complements the traditional flow, providing software flexibility and programming speed. This has led, by the way, to the rise of optimized AI optimized platforms, and we've seen them before. NVIDIA has AI optimized GPUs. We have looked at Intel. We have system on chips that are very much specialized, but we have a new way of using our latest version of Intel Stratix 10 NX FPGA to rethink how we look at DSP blocks, and that's what I will be talking about in the next few slides. Peak tops, like everybody in the industry quotes, are important. They're an important metric, but it doesn't tell the whole story. And that is really what the message that I want to tell you today, because peak tops can be misleading. A very specific compute platform can deliver the promise of these peak tops if, and this is a big if, all the tensor units are 100% utilized all of the time, and there are no system level overheads to get the data in and out of the accelerator. These are big ifs. And as you well know, this is not the case in real applications. And so this is what we do to look beyond the performance for the complete story. And this is what my team's research is based on today. So we have compared AI optimized FPGAs and GPUs based on real achievable core compute performance. And we have measured the overheads in realistic inference systems, as you will be seeing next, for a suite of diverse, real-time, domain-specific, deep learning inference workloads. And so I will be showing you the results. And by the way, this is also part of a paper that we are publishing in FTP, and the paper has all of the details that you can look at and try for yourselves. But here is an overview. We use, as we say, our newest Stratix 10 NX FPGAs, and I'm not going to go into all of the details of the Stratix 10 NX in this talk because it's rather short. But just to tell you that we have high performance AI tensor blocks as part of the core, abundant amount of memory, HBM memory that is very large and very close to the processing. This is very key to minimize data transfers in and out of the device. And so we have high bandwidth networking provided with our chiplet architecture, which have tiles that provide extensibility. And so tensor compute, near memory, networking delivery, all of together to give us high performance hardware optimized AI. So an in-fabric tensor blocks. This is a high level picture of what an FPGA looks like today, where you have traditional columns for DSP blocks, traditional columns for programmable logic, and then VRAMs. We, for NX, Stratix 10 NX, follow a different approach. We replace the DSP blocks with AR tensor blocks. And this way, we revamp the compute for AI without increasing the die size and without increasing the complexity. So the in-fabric tensor blocks replace all the DSP blocks with these brand new blocks that revamp the compute without increasing the die size. And so these are AI-targeted compute nodes that provide scalar, vector, and tensor operations to keep the same interface to the programmable routing. And so therefore, our routing tools can be used, our normal development tools can be used, and it has the same number of inputs and output ports as the normal DSPs. We target AI numerical precisions all the way from integer 8, 4, floating point, full floating point 32, half floating point, and B float. And we dropped some legacy compute modes for performance. And so let me show you how we implement a neural processing unit in Stratix 10 NX. And that is based with a baseline NPU architecture and development flow. Now, again, I'm not going to go into the whole details of this. You can look at the paper, but here is the fundamental architecture of this domain-specific NPU, neural processing unit, where it starts with, at the left-hand side, matrix vector units, which are the heart of the NPU. And this block on the left-hand side is all programmed as an NPU overlay. So the way to do this is that the FPGA bitstream is generated once, and you download programs that you can see on the right-hand side. So these are C-like programs that you compile and you download as you would download any other software, because it follows the same hardware-software contract that I mentioned earlier in the talk. So this way, we're able to write workloads in domain-specific language and estimate the performance using standards tools that we use for C++, etc. And that relies on an NPU compiler that downloads these bit streams. And so it's based on one optimized bit stream that goes into the hardware and then program the NPU repeatedly in software. And so you can imagine that your design cycle now is orders of magnitude faster, because you don't have to wait for new bit streams to be compiled. Instead, you compile C code programs, and then they are downloaded by the NPU compiler into the domain-specific architecture. So that's really the key to increase the performance. Now, I'm going to show you some results. These are different workloads that we ran, compared traditional FPGAs, Stratix 10 MX, GX, and NX, and for a variety of workloads. For some of them, they did very well. For RNN 1792 at 256, over 5 times better performance. And for some other, like GeoMeans, we get 3.5 performance that is much better. So what we find is that the NPU on Stratix 10 NX achieves good performance, but we go beyond the original performance by using the new extensions that we provide with Stratix 10 NX. But we didn't stop there. We went ahead and we said, okay, what about if we compare to traditional devices? And before I move on, I want to summarize. So we have very low latency, over 30 integer 8 tops, and the NPU is almost fully utilized. And utilization is a very important aspect because of what I'm going to show you next. So we went ahead and we said, well, let's take a look at what happens if we compare different workloads with other devices. Here, the red line is NVIDIA T4. The green line is NVIDIA V100, and the blue lines is our NPU run on Stratix 10 NX. You'd be very surprised that for relatively low batch numbers, we perform better than GPUs. And the reason is in the right-hand side. The reason is that our utilization of the device is much, much higher than a GPU. And at batch results, even though, as you can see here, at 256, at batch 256, we do reasonably well. The reason is that you may have a very powerful GPU, but if the GPU is not fully utilized, then you're wasting performance. And so our results show that we can get 24 better results compared to T4, 12 times better results compared to V100, and very competitive at high batch 256, as you could see here from the graph, which improves the higher utilization in all the cases. But again, we didn't stop there, and we looked at energy as well. And so we measure energy, and we know that the energy is at least 12 times better energy efficiency than T4 and V100. And so these are real world solutions that we have investigated. At the system level as well, here are comparisons with the system level, where with an implementation with Stratix 10 NX, we have no initialization overhead. And so you can see here, where we compare initialization, the data transfer in and out, and the core compute. All of them favor this implementation using an NPU on a Stratix 10 NX device. And the reasons are very clear. The high memory that is inside NX can be utilized to improve the performance of data in and out. Data locality improves, and therefore the results that you see here, where we compare very favorable with at the system level with other implementations. So 20 times improvements compared to V100, about 5 times improvement on V100 on the RNN size, both in execution time and on the sequence length here. 10 times and 2 times less system overhead than the these very well-used GPU systems. Again, I emphasize these results are real-world results that rely on the fact that most systems use either low batch or lower batch and data locality, and therefore GPUs are highly underutilized in many cases. So the summary is that the AI tensor blocks in our Intel Stratix 10 NX significantly increase the peak tops, and so that takes us to peak performance, as we say. So comparing an NPU on Stratix 10 and NX to a non-optimized Intel FPGAs for AI, we see that at least 5 times better performance using INT8 multipliers, and at least 3 times higher average performance across all of the family. Comparing the NPU on Stratix 10 to AI optimized GPUs like the T4 and the V100, we see that for batch 6, which is reasonably a reasonable number, we get 12 times better performance to 10 times energy efficiency, as well as T4 and V100. So these are, we are fairly certain of these numbers because we run extreme number of tests using these systems. So now let me tie it up with how this ties up with delivering cross-architectural performance and oneAPI. Now, you've seen how for a very specific solution, we can provide extreme efficiency by establishing a domain-specific architecture, implementing a hardware-software contract through an ISA, creating the hardware bit stream to be downloaded on the FPGA, compiler, if you will, a domain-specific language, a DSL, that runs this domain-specific architecture, and then improve the performance. So that's one solution that I've shown you using an NPU. Now, how do we tie it all together? That's where oneAPI comes in. Because even though these are AI-optimized workloads, we have diverse workloads that require diverse architectures. And so we take a very realistic view to the solutions, that for many workloads you may require a CPU for scalar type of problems, vector architecture implemented in a GPU, a matrix-like architecture with dedicated AI chips, and spatial architectures that are critical for FPGAs. The future is very diverse, and it has to be a mix of scalar, vector, matrix, and spatial architectures. And that is just simply the reality that we live in. Heterogeneous systems are here to stay. But that brings programming challenges, because how do you address multiple architecture? You have separate programming models and separate tool chains for each architecture, which requires separate training and licensing and compilers, etc. You know very well this is a challenge. And not only that, you need to be able to debug and monitor and maintain each of these different architectures. And to top it off, it's very difficult to integrate across proprietary IPs and architectures, and there's no code reuse. So even though I've shown you today that domain-specific architectures, NPUs are great solutions for AI optimized solutions. It is not, it is just one point solution. You need to look at the whole entire system. And that's where these challenges come up, where you have multiple architectures to take into account. So that is a challenge. And that's where we need a unified programming model that addresses all these multiple architectures. So this is what oneAPI comes about. I'm not going to go into all of the details of oneAPI, but just to tell you from a top level theoretical view, why is it that we decided as Intel that this was a problem worth solving for everyone based on open standards, so that we can guarantee a common developer experience across all of these multiple architectures while providing uncompromised high level performance on all of these architectures. Now, don't get me wrong, this is very hard problem, extremely hard problem, and we are in the process of solving it. We're not saying that it's completely solved, and that's why it relies on industry standardization and open specifications, because we realize that one company cannot possibly provide the solution. And so it's a community that is going to help bring all this unified model, but we're laying the foundations. We're putting the road so that we can all work together into this. But what we have today is reduced development time with host side compilation and emulation reports. We have used our vTune profiler to improve the debug and runtime analysis across all of these platforms, and we could use code reuse. Code reuse is a very important aspect, as you well know. And so this improved development ramp up and training, because you don't have to train for different architectures, is key. And so we want to provide this one level of performance that you could see here on the right hand side. So you have application workloads that needs diverse hardware on top of all the middleware frameworks that are used today, and that relies on top of this one API that has a compatibility tool, languages, libraries, and analysis and debug tools all together on top transparently over all of the XPUs, as we call them, the multiple device architectures. And of course, it is available for FPGAs as well, where on the left-hand side, you see a typical application that is optimized on the frameworks, and the oneAPI product provides direct programming, which is done through data parallel C++, DPC++, and an API-based programming based on libraries that take analysis and debug tools, and that is part of the oneAPI problem, oneAPI product that solves the problem of these diverse number of architectures. So direct programming is one way, and libraries is another way. So you take your source code, and then you translate it into something that can be used across many devices. And it is a traditional front end that will feel very familiar to developers across. So let me stop here, and just to remind you where we have been. I've told you about all the different architectures that can be implemented by thinking of your problems in terms of domain-specific architectures using flexible overlays, using FPGAs. I've shown you how our specific solution for AI-optimized platform now relies on tensor blocks that are key with Stratix 10 and X. And I've also shown you how Stratix 10 and X can make a big difference because of the high bandwidth localized memory, and how we all tie it all together with oneAPI. So let me start there at 29 minutes from my talk. Thank you. And I'm gonna, in the 1 minute that I have, I will take some of the questions that are on the chat. Let's see. Batch size. Batch size is essentially the number of data elements that you take at one time in a framework, if you will. And so and so large chunks of data require far larger transfer, and data locality works much better for smaller batch size. Many applications today are low batch size. In many cases, it's batch one, where you take one data at a time. But our research has gone, as you have seen today, in working on relatively good batch sizes, all the way to 32 and 64 chunks of memory, all the way to 256. So it has to do with memory locality. Okay, I think that's all the questions that we have today. Thank you very much, everyone, and I wish you a successful rest of the conference.
Thanks, Jose, for a wonderful keynote. Thanks for your time. I know it's late evening. Firoza ma'am, yeah, now we have Dhimant here with us from Intel. He's Intel Fellow. Firoza ma'am or Gaurav sir, can someone take up and introduce him first?
Sure, thank you, sir. Due to some academic engagement, sir is not present right now. So on behalf of Dr. Gaurav Trivedi sir and Aryabhatta Sahu sir, we would like to introduce Dhimanath Nagaraj sir. Sir is the fellow Intel. Sir is an Intel fellow and architect working on custom logic and new product innovation in the data platform group at Intel Corporation. Based at Bangalore Design Center in India, he leads effort in product innovation that target emerging computing usage models across server CPUs and Intel-filled programmable gate arrays, FPGAs. Nagaraj sir also co-leads the India Site Technology Office. Since joining Intel in 2007, he leads multiple generations of Intel Xeon processors-based server CPUs from concept to productions. He also leads the architect for data center discrete GPU product. Among his key contributions, he helped Intel to conceive the Xeon D processor, a density optimized and low power product line for the hyperscale cloud networking and the storage market segment. He is a recipient of 2 Intel Achievement Award and the company's highest recognition. He also earned his BTech degree in Electrical and Engineering from National Institute of Technology, Surathkal, and a master's degree in Electrical and Computer Engineering from Purdue University. He holds 9 patents and also a frequent speaker at different industrial events. With this, we would like to invite Sir to please start with the keynote session. We'd also like to inform Sir that we have made you the host, we have made you the presenter. So I would request you to please, Sir, check if you are able to share the slides.
Can you hear me all right?
Yes, sir, we can hear you properly, sir. Your audio as well as video is very much clear.
Okay.
So,
thank you. Thanks for the kind introduction. Let me just
thank you, sir.
Share and let me know. Can you see what I'm sharing?
Yes, sir. Your slides are visible, sir.
Okay.
Yes, sir.
Thank
Everything
you.
is fine. Yeah. Thank you, sir.
Yeah, thank you. Good morning to all of you. It's a pleasure to have the opportunity to engage with this august set of faculty and researchers from various universities. My colleague Jose has provided great insights into where the spatial architecture and heterogeneous computing is moving, and what's the relevance of the programming model challenges and so on. What I thought I'd do is maybe take a step back and paint a broader brush on, where are the technology trends and challenges if we look at it from, edge to cloud. Okay, and by the way, if my audio drops or if the presentation drops, do let me know. Okay. All right. So.
Dhiman, we can hear you. Please continue.
Okay, all right. So in terms of agenda, I think we have about 45 minutes. I have a lot of content, and I'll try to modulate depending on how things go. So first, I'll touch upon some industry trends from cloud to edge to network transformation and so on. And then once we talk about some of these trends, it might be insightful to then look at how are we as product designers and technology providers, how are we responding to it? What are the things that we have at our disposal? But at the same time, what are some of the challenges that we collectively, right, as industry and the academia have to solve? I will touch upon some collaboration opportunities and then close with a summary. Okay. So no surprise, one key observation that all of us will identify with is the increasing workload diversity, right? When you start looking at the various domains, it could be consumer, healthcare, finance, transportation, you name it, right? And in there, you can talk about specific use cases and workloads. It could be, chatbots and search in consumer. In healthcare, it could be, drug discovery and, diagnostics and precision medicine and so on. In finance, it could be things like risk mitigation, algorithmic trading. You get the hang, right? So the diversity of workloads is immense. But the one thing is that, independent of what these workloads are, actually I think moving the slides is a little slow. But what I would point out is that independent of what these workloads are, whether they get deployed in a cloud environment, in IoT, or at the edge, increasingly these are getting enabled through AI. Okay. So my slides are not advancing. Isra, can you actually see this? I'm not able to advance my slides.
I can see now. You have to go in presentation mode. So
yeah. Maybe I'll just try this, because in presentation mode it's taking time to advance. Let me try.
Okay, sure.
Okay. All right. So the next key observation, again, no surprise to all of us in the technical and technology domain, and as users, we are generating data at a faster rate than the ability to analyze, understand, and transmit, and more importantly, secure and reconstruct it in real time, right? And this data could be generated by the plethora of IoT devices that we have, and by some account 50-60 billion of them. It could be, it could be industries, it could be aircrafts, it could be smart cities, right? But the amount of data that we are generating is staggering, and by 2025 we expect 275 zettabytes, right? Zettabytes of, and what's the 10 to the power of like 21 amount of data to get generated, right? And this is important because like we say, data is the new oil. We do talk about how we can use this data to draw new insights for all those domains that I talked about, right? It could be for healthcare, it could be for transportation and so on. But the ability to store this data in a secure way, the ability to mix and match multimodal data, the ability to basically have an architecture that says, is this, do I need to access this frequently? Do I need to push it all the way to the cloud? Do I need to filter it? You start thinking about those, and this becomes a very pertinent problem, right? So data ingestion, data storage, security around it, all of this becomes very pertinent problems. Okay, and then when we talk about AI and compute needs, the next observation is really the insatiable demand for compute, right? And this plot is really trying to show how the compute demand has been growing, and not very long ago, right? And I'm not talking about neural networks, we've been talking about it for maybe 30-40 years, but even as recent as 2013, when we first started talking about AlexNet, and we started looking at accuracies in the realm of human accuracies, right? From then to now on, right? And again, now we talk about GPT-3 and so on, which is I think 175 billion parameters, right? But if you really look at the petaflops per second day, it is a staggering amount, right? So there is in these maybe 7 to 8 years, there has been a 300,000, right? I'll say it again, 300,000 increase in compute demand. Okay, so something like AlphaGo that DeepMind developed, what used to take, really the challenge here is it takes if you have an exaflop, right? If you have an exaflop computer, it may take you 2 days to train that model. But really the challenge is, we really need to train it in hours and minutes. And for that, you need, 100 exaflop kind of a machine, right? And really, if you really look at this, the trajectory continues, and it continues, every 3 to 4 months, the compute demand for training these models is doubling. Okay, and putting it into context on an example that many of us may be familiar with, right? When we talk about something like population scale healthcare, right? And here I'm just showing what are some of the things, right? When you talk about, you might have heard this term called omics, right? Which is a combination of genomics and proteomics and metabolomics and so on, right? So basically, you may be working on sequencing DNA, it could be human genome, it could be human microbiomes, and right, everything from molecule to genome to organ level. Working with these data sets and delivering the throughput, this is, the data sets is an order of a billion kind of a problem, right? And then creating these AI pipelines for you to be able to correlate these different data sets and draw insights, coming up with a data-centric compute platform that is open, that is scalable, that is secure. We talked about storage, the ability to store all of this in a tiered way. And at the end of the day, you need to be able to deliver these solutions about this genome sequencing. And many countries are doing that, right? They're doing population scale genomics. They're creating electronic health records and so on and so forth, right? And so a lot of this gets used for drug discovery. How do you do it in a way that it is cost effective, right? The total cost of ownership in doing every sequencing and actually extracting the metadata, doing federated learning, all of this has to be done in an easy to use way. And, Jose was talking about the software stack. It becomes important for a problem like this. It is a really challenging problem. Okay. Now, how is all this compute being delivered? Again, we all know that cloud computing has become mainstay. And what is now happening is that to be able to deliver this level of compute, it is becoming warehouse scale, right? When you talk about the hardware, the software, the networking involved with it, the operations, the facility, all of these are tightly interwoven in a way that the data center as a whole is becoming a computer, right? Because when you throw a HPC problem at it, or when you throw a machine learning training problem at it, this entire set of resources could work together as a single computer, right? And with that comes a bunch of, depending on the workload and usage, the feature attributes that you need to deliver. There are real problems around, when you virtualize and containerize, and you can have hundreds of containers running on one CPU, right? We don't think about a CPU or one platform anymore. It is at data center scale. How do you ensure quality of service? How do you ensure reliability, availability, serviceability? What about the security, right? And what about things like power management, right? We talk about exascale compute, but that takes tens of megawatts of power, right? It can light up a small city, and there is a long way to go in actually realizing the ability to make it, true utility, right, in terms of power efficiency and so on. Okay. So we can't, talk about cloud without talking about what's really happening at the edge. So edge is now the epicenter of innovation, and there are multiple drivers for edge, right? There are as we talked about, there are, by some account, very soon, maybe 100 billion smart intelligent devices. They're all generating data. The use cases, it could be in terms of real-time use cases for a smart city, or in terms of Industry 4.0, where you're trying to do real-time, quality assurance and so on. These use cases, when you have so much data, you can't push everything to the cloud, right? It has to be, you don't have that much bandwidth. The latency at which you have to deliver these workload use cases is small. So like, for example, so the compute needs to be close to where the data is getting generated. You may not have ubiquitous connectivity, right? So a lot of the processing might need to happen at the edge. And so by some account, by 2020, 45% of the data will be stored, analyzed, and acted upon at the edge, right? Without having been pushed to the cloud. Okay. So your ability to orchestrate these use cases in this distributed environment across edge and cloud, and in a way so that you can deliver the metrics for that any particular use case. And it could be, these days we even do like robotic surgery and telemedicine and so on, right? So a lot of these very mission critical use cases, it is a real challenge. Okay. And then we can't have any technical talk these days about technology trends without talking about 5G. And this is going to be disruptive, right? Because, we are now talking about compute that's going to get fluid, it's going to get intelligent, and it's going to get pervasive, right? And so it's really a fully connected, mobile, and end-to-end smart society, right? And so I'll just talk about a few things in terms of what this is really disrupting. It's across the board, right? It could be in industrial 4.0, it could be in transportation, things like machine-to-machine communication, and how do autonomous cars communicate with each other, with the cloud. It could be in healthcare, like we talked about. It could be in the space of media. It could be in the space of retail for improving your inventory management and user experience. All of this will be unleashed through 5G, right? And again, these numbers are staggering, right? Going from 4G to 5G. When you talk about 1000x in data throughput, right? 100x connected users per square mm. This is related to 4G, right? 50x peak data rates, 10x reduction in latency. If we deliver to the promise, this is going to just open up some very, very potent usages that will change the way we lead our day-to-day lives, right? And so again, going, just looking at how this has happened. If 2G enabled, you went from analog to digital, and you maybe 3G enabled data and internet from voice to data for the first time. 4G enabled broadband. 5G is all about doing the following, right? It is not just your smartphones communicating with each other. So it's not just user to user communication. It's also ultra reliable and low latency communication, right? And it's also machine to machine communication, right? And all of these provide practical problem statements. It could be in your communication networks. It could be in how you process this, how you make it real time, right? What is the power at which you deliver this? There are some real potent research problems here. Okay, or it could be even in terms of how the network is transforming, right? So you might have had a legacy network which was largely built out of fixed and purpose built. It could be a firewall and so on and so forth, right? Which were purpose built hardware for a particular function. It is moving to a world of software defined networks, and all these network functions are getting virtualized, right? So it's really software running on standard hardware. And when that happens and you take to the next level and say, it's going to look very similar to cloud, right? The network is going to look very similar to the cloud. And so this is what we are calling cloudification of the network. And with that, you get intelligence when you need it. You get the flexibility and agility of the cloud. You have a single scalable architecture that can deliver all these use cases. And we talk about 5G. One of the aspects of 5G is network slicing. So your network can be sliced so that you provide specific slices for the use case that you want to deliver. So lots of new interesting services, right? And so the challenges here are and the potential here about this whole distributed network and the convergence of compute and communication, because it's not really cloud sitting somewhere in 10 or 20 data centers far away from you. It is permeating through the network, and you will have compute, and pretty soon maybe even petaflop compute very close to you, right, for you to use. And then use cases have to stagger and get deployed between these distributed compute networks. Okay. So again, I think the other key trend and challenge, and the data may be a little dated, but no surprise, right? Any CIO survey that you do, cybersecurity is at the top of your mind. There's not a day that passes by where we don't think, see news, where we don't see news about data breaches and hacks and ransomware and right, and so on and so forth. And in just the amount of spend to secure everything from the hardware to the software to the network, right, is a humongous amount, $1 trillion by 2022, right? And so this must be something that we prioritize. It, this is the bedrock of our system design. Anything that we talk about building, it could be hardware, software, network, and even in the software, it could be the operating system, it could be firmware. Attack surfaces are all over the place. So security must be the bedrock of anything that we talk about, right? And again, this is, and I'll touch upon it later on, right? This is also an excellent field for collaboration, okay? So now when we move on to product design trends, so I like to think of it as, technology disruptions drive inflection points, and maybe every 20 years you have major inflection points, right? So if the 80s was around, digitizing everything, so it's really where microprocessors became mainstay and you had personal computers and so on. The 90s was more about, internet, so you network everything, and then you have mobile everything, and then it led to cloud everything. So internet and cloud, and then the next 10 to 20 years, and we are just at the cusp of this inflection point, is around intelligent everything, right? And so technology in terms of digitization, in terms of software, in terms of mobility, in terms of AI, is actually driving these inflections, right? And so really you see on the Y scale, the compute, like I said, right, is growing from, and if you really talk about the first microprocessor, right, maybe the 8086 to where we are now, right? We are talking about zettascale compute, okay? So how is all this powered? So the foundational aspect of all of this continues to be Moore's law, and in spite of all the naysayers, and in spite of all the challenges that we have, many times you look at it and say, how can you beat physics, right? But our researchers, right, and again, this is collaboration between material scientists and architects and device physicists and circuit designers and packaging innovation folks and so on. Anytime you hit a roadblock, right? You went from a 2D transistor architecture to strained silicon, to your dielectric material became high K, to FinFET, which is 3D, and super FinFET that Intel just talked about, right? And in terms of feature sizes, right? So everything from frequencies going high to what do you do on the capacitance to reduce power, what do you do on the interconnect to reduce the interconnect wire length, how do you stack it up, right? And again, while I'm saying all of this, these continue to be problems. You may be reducing the voltage of operation, you may be reducing the capacitance, but at the same time, you're not seeing Dennard scaling. Your compute or your power density is growing, and so there are lots of challenges around how do you cool, what are the packaging technologies. So again, while we are generation to generation solving these problems, and just to give you right, we are continuing to push the boundaries of innovation. And just to give you some perspective, right? So what has Moore's law done and continues to do? These are all staggering numbers, right? The transistors, number of transistors per square mm has gone up, what is it, like 10 million times, right? Or 100,000 times, right? The cost of transistor has come down 10 million times, right? It could be a wafer sizes, your frequency of operation, the number of cores that you're using in a CPU. While all of that is happening, at the same time, your fabrication costs are growing. So it is, this industry is going to consolidate, but at the same time, it is ripe for innovation, right? Continued innovation. And so if you really, it's not just about Moore's law and process. You take any aspect of what is driving this, right? It could be in the way we do IC design, right? So how we did logic design, right? When we had hand-drawn to Carnot maps, to circuit design and synthesis techniques, to hierarchical design. So the whole, EDA industry, to what's happening on the architecture space, right? You might have had single-thread CPUs to multi-thread CPUs, right? To multi-core, and now you have massively parallel GPUs, and Jose talked about spatial compute and FPGAs, and you have domain-specific ASICs. We continue to, right? Anytime a particular architecture hits a plateau, we innovate, right? And so this is the S-curve of innovation, right? And so when you start superimposing each of these S-curves, you get exponential growth. And same thing with software, right? From assembly to C to Perl and web-based and all the languages we have with for machine learning now, right? So this is the S-curve of innovation, right? So we are constantly innovating as industry and academia to service the needs of these demanding use cases. Okay. So Jose also touched upon this. What we are seeing is that with this plethora of workloads, you need a diversity of architectures to support it, and you deliver to these architectures in many ways, right? So CPUs traditionally have been great at scalar compute and task parallelism. GPUs are great at vector compute, but you also have vector engines and specialized vector execution units that you pull, like for example the Intel AVX, right, that you pull into the scalar to augment vector, right? But if you want pure vector compute, then you have GPUs. If you want matrix compute, you have a lot of these purpose-built AI, matrix optimized, right? Matrix compute or matrix vector compute optimized kind of architectures. We also talk about bringing some of these specializations into the CPU, like I said, through instruction sets and execution units. And then spatial, of course, right? Spatial continues to disrupt. There are lots of workloads that Jose was talking about that are suited for spatial architecture, right? And FPGA is your quintessential spatial architecture, right? And so really, you have diverse use cases, diverse workloads, and you break down the workloads, look at it. You need a combination of these diverse architectures to support these workloads, okay? So another perspective around how these things get deployed, right? And so it's really about saying that, do we understand what we're actually looking at, right? So for example, if I'm a cloud data center providing infrastructure as a service, I don't really know what kind of workloads might run, right? I mean, I might have AI workloads, I might have some kind of database workloads, right? I might have graph workloads, I might have some HPC type of workloads. So when you look at that, when you look at, is it getting deployed to the cloud or it's getting deployed at the edge, you have a certain set of compute solutions. The CPUs are great when, AI may be a big portion of your workload, but you're not dominated by a single type of workload, right? You may have tens or hundreds of workloads. The CPU is your workhorse, right? And from an Intel perspective, we have our Xeon CPUs for the cloud and for the edge, and then you have a variety of other kind of architectures like Atom and so on, right? And so then when you go look at it and say, well, my workload diversity is not that much. Maybe I only need to care about deep learning and high performance computing and graphics and maybe some real-time media. Then maybe you deploy a combination of CPUs and you deploy, something like the GPUs, right? From Intel perspective, it's the XE architecture. Other, industry players have other architectures, right? But then you look at it and say, hey, but what about, if I know that my workload is super specialized, and I can actually build a dedicated appliance for it, and maybe I'm deploying it in the cloud, and I'm doing both a combination of training and inferencing. I'm doing just inferencing at the edge, or I'm doing some kind of in situ training and inferencing and all of this, right? So depending on your form factor, depending on your power, depending on your thermal profile, depending on your how much compute you need, and from edge to cloud to across the board, you may have a combination of CPUs, you may have a combination of GPUs, you may have a combination of purpose-built AI engines like the Habana engine that is now offered from Intel, and some of you might have seen the announcements with Amazon and so on that's deploying Habana. Right, and you can also have FPGAs, right? FPGAs, like Jose was showing, right? There are lots of these networks that perform great on FPGAs. Okay, so so really, if you look at it, heterogeneity is the order of the day. Jose touched upon this. At the bottom layer is where you have the transistors and these different architectures, right? CPUs, GPUs, FPGAs, interconnect, memory, all of it. And on top of that, you need to have some form of abstraction such that the firmware and BIOS and drivers, abstract the hardware for higher level software, right? And then you might have your operating system and your virtualization and orchestration layer. And we just call these, level sub-zero, which is fundamentally what is required to abstract the software, the hardware. How do you present it to the next level of the software? And then what are the other frameworks and runtimes and so on. But, really, if you think of it, it's a fairly complex end-to-end stack from solution and application down to middleware and runtime and virtualization layers, the OS to the drivers, all the way to the hardware, right? And so managing this, right, and then like Jose was saying, how do you do this in a where it's done in a productive way, it's done in a performant way, and it's industry standard, right? So that it is done, and I'll talk about that in a little more, but in an industry standard, so using something like data parallel C++ and so on, right? So that the ecosystem can innovate, right? That is the challenge upon us, and we are making a lot of great inroads into that. Okay, then I will quickly talk about it's when we talk about Moore's law and how the devices are enabling denser compute, right? Packaging technology is also disrupting because you still are limited by how big a chip you can build, right? It's a reticle limit, maybe 800 square mm or so. But advanced packaging is allowing you to break those barriers, right? So if you really go from standard packaging to 2.5D packaging to 3D packaging, right, where you stack things 3D and interconnect it in a fine bump pitch, what you see is that the bump pitch of the packaging interconnects, the bump density, and the power, right, the picojoules per bit to transmit a bit through that interface. All of those are advancing, right? So your bump pitch is going from 100 micrometer to less than 10 microns in the future, right? Your power picojoule per bit is going from 1.7 picojoules in standard package to all the way to 0.5 picojoules to 0.15, and we are really working on technology that will get it to something of the order of 0.05 picojoules per bit, right? And so while you bring this together, you can build extremely complex products, right? We have this thing called Foveros technology, which is 3D stacking, right, where the bump pitches are tight, and you can stack chips built on different processes. And why do you build chips on different processes? Something maybe you may need high speed, something else maybe need low power, something else may need special analog circuits and special analog devices that are more conducive to a certain process variant. So you can build chips on different process variants, and you can bring them all together through advanced packaging, right? And so from an Intel standpoint, some of the products that we have brought out in the last, say, 5 years, some of this is really staggering advancements, right? So if you look at, for example, something like the Agilex FPGA and Stratix that Jose was talking about, this is 2.5D, right, where you have your FPGA core fabric as one chip, and then you have a bunch of maybe transceiver chiplets or other accelerated chiplets that attach to it through embedded bridge kind of an interface, right? Or you can have 3D stacking, and Ponte Vecchio in particular is going to be our foray into exascale compute. And this one is a true technology marvel, right? It has 50 plus pieces of silicon in one package, 50 plus, right? And if you like add up the, whether it could be the different technology nodes, it could be 2.5D and 3D stacking coming together. It could be, things like the total amount of silicon, right? Thousands of square mm of silicon. You're not limited by the reticle anymore, like I said. How all of these comes together to deliver a system in a package, right? So a lot of innovations happening here. But at the same time, when it comes to how do you cool this, because when you talk about Ponte Vecchio and these kinds of compute that enables exascale, you want to be able to increase your compute density, but that comes with power density increase. How do you cool, right? Right? How do you reliably build these packages, right? How do you keep cost under check? So lots of interesting challenges here, right? And then when you start talking about the system design side of things, no surprise, right? We constantly hit the memory wall. when you look at the amount of compute, it comes with insatiable amount of compute with memory bandwidth. And it's not that you can deliver this memory at unconstrained power, right? Because like I said, if you look, if you put you have constructs where the memory may sit within the package, it may sit outside the package on the system. But really, if you delivering these high bandwidths, we have anywhere between a 5x to 10x gap on power efficiency, right? This is where we have to innovate. And just putting it into perspective, right? When you look at the memory hierarchy, you have everything from caches, right, which could be order of a few hundred megabytes, but the access latencies are an order of nanoseconds, all the way to in-package memory, which could be gigabytes of memory, and the access latency could be tens of nanoseconds, to the DRAM memory that we are all very familiar with, to storage, right, to secondary storage and tertiary storage, right, and it could be solid state drives or magnetic tapes and so on, right? So when you look at all of this, for the kinds of usages that we want to deliver, this could be usages at the edge, this could be usages in the cloud and in high performance deployments. You often hit capacity gaps, like for example, right at the memory level, right? You would want to have much higher capacity memory, but not really with storage semantics, but with memory semantics, right? So how can you get storage kind of capacity, but with load store kind of latencies, right? Instead of doing like a file IO and taking a context switch and having a high latency event, right? So we have delivering this capacity with memory semantics. There's also storage performance gap, and Intel, as an example, is looking to solve this with persistent memory and 3D crosspoint and innovations that are happening in the NAND technologies and so on, right? Where you are disrupting this hierarchy with new memory technology, but the challenge persists, right? We still have a challenge in terms of wanting in this hierarchy at various levels 10x the capacity, 10x the bandwidth, 10x lower latency, 10x lower power, right? So it could be in new types of memory, it could be in new architectures, it could be in terms of software that can use this different memory hierarchy. So it has to disrupt and deliver to this promise. Okay. So then quickly talking about software, because it's really software that unleashes, you can build all the hardware that you want, you can make it dense, you can make it, high performance, but to really realize the promise of the underlying hardware, software has to equally keep up pace, right? And what we're seeing is that, writing performance software is increasingly becoming painful and expensive, right? And this could be, just by the way, the complexity of the different modules. You take any business logic and talk about how many different modules need to come together, right? How do you actually parallelize? If you're talking about HPC installations, how do you extract parallelism from the hardware, right? How do you make it such that you orchestrate it, so that you are putting data close to where you have memory, or where you're shipping functions where close to where the data resides, whichever way, right? With the new paradigm is shipping functions where close to data resides, rather than distributing data to where compute resides, right? So managing and so on.
Excuse me, sir. So your voice is not clear. Yeah.
Okay, is
in
it better
between
now?
there was some disturbance in the, yeah, now it is okay, sir.
Okay.
Thank you, sir.
Okay. So I was saying that, productively writing software and deploying it, there are some numbers here, right? The spend is a big number, right? And so there's a lot of, and then when you apply to specifically around AI, that becomes even more pronounced because of the scale at which it needs to get deployed. But what if we build a virtuous cycle where you design hardware and software for AI, but you use the same AI to in turn design software and hardware, right? So it becomes a AI you're helping and speeding up AI, and the AI that you're deploying is in turn helping speed up your hardware and software design, right? So that is the virtuous circle that we envision, and this is just one example of some work that Intel is doing with MIT and in collaboration with Google and Microsoft around machine programming, right? Traditionally, the human programmer is known to own not just the intent of what that program is supposed to do, but the algorithms and the data structures on how you deliver to that intent and the actual implementation, right? But what if you think about a world where you just as a human provide the intent and the machine takes care of the algorithms and the data structures, and this is happening today, right? I won't go into a lot of details, but there is a collaboration happening. So look at this, D sale and C sale, right, with MIT, and there are some examples of certain algorithms having been designed by the machine, right, and how it compares with when you design it, when a human designs it. So this is a important area of future-looking research, right? And then I'll speed up a little bit. I talked about security, and security again, the attack surfaces, everything from hardware to BIOS to even your hypervisor, right? You can't trust your hypervisor, right? You have all your containers and guest VMs and so on. It's not to say that the hypervisor is pristine, right? So how do you make it such that all of these attack surfaces are protected from application down to the hardware? And there are many examples of attacks happening, right? It could be privilege escalation attacks, it could be side channel attacks, it could be firmware getting compromised, right? And so this is a very pertinent problem. And so you have to protect data at rest, you have to protect data in flight, you have to protect data in use, you have to protect, basically there is authentication, right? There is encryption, there's authorization. All of these, right, have to come together, from edge to cloud. And all of this, it's not that, in the name of security, right? Obviously, it has to be secure, but your performance cannot tank in delivering that security, right? So how do you, while you're building this more and more sophistication into securing these different attack surfaces, how do you make it such that the performance doesn't suffer, right? And that's where you have all these technologies, right, for encryption. For from Intel, for example, you have total memory encryption, you have software guard technologies. I mean, the ability to create enclaves where you can run code, the ability to harden the firmware, trusted execution where you measure your environment and then before you actually execute trusted code, and then acceleration technologies, right, like quick assist. Let's suppose you want to accelerate your crypto encryption, right? It could be any of your ciphers, right, or it could be IPsec and and so on and so forth, right? So you have accelerators as inline and look aside accelerators. You may also have instruction sets, right? So that you constantly enhance the instruction set of the CPU. So you look at, for example, let's say an RSA algorithm to say, okay, what kind of constructs are actually getting causing the performance bottlenecks, and you create a specialized instruction to actually natively support it, right? So again, looking forward, once quantum becomes real, cryptography is also going to get disrupted, right? Both symmetric and asymmetric. Today we have all of these, AES and SHA type of algorithms, but these will get weakened when quantum computers become real, right? So you can go look at increasing key sizes, but you can potentially, right, really break these algorithms when quantum becomes real. And so, what is the solution for post-quantum cryptography, right? Also a very important domain of research. Okay, so I'll try to quickly touch upon some collaboration opportunities. Again, I just provided a broad brush here. The whole aim is to support digital democratization, right? And Jose talked about Intel oneAPI, which is looking to solve this problem of heterogeneity and how do you create software in a productive way, in a performant way, and in a open way, right? So that the whole ecosystem can contribute. That's oneAPI. Intel FPGA University, again, a lot of the initiatives like this collaboration that we are having with you is through the Intel FPGA University. And then we have a startup program because the innovation cycle is not complete without bringing in startups. And many of your own universities have incubators and accelerators, right? And so I won't go into the details of Intel oneAPI. Jose covered it. Again, the Intel FPGA University, everything from curriculum development to workshops such as this one, to high impact research, to partnership, bringing in both the academia and the startups, right, together. And there are some examples here, right? So we have in the Intel Startup Program, right, many successes around, helping startups in the quantum space, in the healthcare space, in the manufacturing space, and in the oil and gas space, and so on. Okay, and this is just an example, a recent example of the close collaboration between Intel and the government and the government labs and the academia, where in the COVID diagnostics space, we together built an end-to-end diagnostics setup, which does very fast testing, and it also has genome sequencing in the pipeline just to understand all the various mutations that can be happening. It also does applies machine learning to be able to understand the risk stratification of a given patient, right? And it also provides the the ability to use this data for drug discovery and vaccine discovery, right? So this is a recent example. The other thing that I'm also very passionate about, right, is around road safety and smart mobility, right? So Intel in India has worked with the academia and the government to come up with a India driving data set, so that we can actually do research around what are the road conditions and apply it to in India. When we talk about smart mobility, it's not so much about autonomous driving, right? It's going to be a few years before, or maybe a decade or whatever, before we see autonomous cars going up and down our cities, right? But you can apply this technology for road safety, right? And so the vision is around what we call Vision Zero, right? So zero lives lost to road accidents, right? So a lot of opportunities in the healthcare space, in the smart mobility space, right, to come together. So I'll end my talk here. I think we are kind of out of time. So in summary, the demand for compute is insatiable from edge to cloud. We talked about it gets deployed in various form factors with different system architectures. Moore's law and chip design will continue to turbocharge the era of AI and 5G, and you're going to have heterogeneous compute, domain-specific accelerators, and the CPU will continue to advance, right? And then you need innovation across silicon packaging, power delivery, all of these to come together to continue to deliver to this trajectory. End-to-end security, software development, productivity, all of these are foundational, right? And I would say, we are at the cusp of this new intelligent era, right? It's an exciting time for the industry and the academia to come together, collaborate, and break the barriers of the various challenges that we talked about. It could be in AI, it could be in 5G, the use cases develop. It can support, right, in software, right? You name it, in security. A lot of population scale problems that we can come together. So with that, I would say thank you for the opportunity to talk to you, and have an excellent remainder of the program, right? So I look forward to the strong collaboration with all of you, as we get more and more opportunities to work together. Okay, thank you.
Thank you, sir, for such a wonderful talk, sir. The participant really enjoyed your session. So thank you on behalf of all the Electronics and ICT Academy across India. So with this, we are coming to the end of the second session of day one. Before starting with the last session for day one, we would request participants to take 5 minutes of break. And there are a few important announcements for all the participants. We request you all to please note that we have already shared the invite link for this WebEx to all the registered email ID. So I request you all to please check all mails before putting any query. We are also receiving requests for the recorded session. I would like to inform you all that we are already having the YouTube live streaming. The YouTube live streaming sessions will be available in the E&ICT IIT Guwahati YouTube channel. So this live streaming lectures will be used only for study purpose. Anyone who is viewing the YouTube live channel and are not joining this event, the attendance will not be marked. So I request all the participants to please use the YouTube link for the study purpose, for reference purpose, and please join by using the link that we shared with you in your respective email ID. Also, throughout the session, we received many requests regarding the attendance. I would request you all to please note that the attendance will be only marked against the registered email ID. So the email ID that you have used for the registration, we will be only considering those email ID. So this is an humble request to all the participants to please join the event by using that link. We are receiving many requests regarding the installation of the software. I would also like to request you all to please check the schedule which is uploaded in the website. The installation guidelines are already provided. And even after going through the guidelines, if you have any issue, then I would request you all to please drop your queries in the Q&A section. Our experts are always available to address the same. And the last announcement is that we are having 2 MCQs on every Thursday. So I request you all to please go through the sessions and please be ready for the MCQ. The MCQ will be as per the scheduled timing and there will be no change. We receive many requests regarding the rescheduling of the MCQ. Please note that we are having participants across India and it is very difficult for us to reschedule the MCQ. So the MCQ we will schedule as per the timings being given in the timetable. So please refer the timetable for the same. So with this, I would request the participant to please take 5 minutes of break. We will be starting sharp at 11 a.m. with the last session for today. Thank you.
Thanks, Dimant, for your time, and thanks, organizing team. So after 5 minutes, we will meet.
Yes, there is another small announcement. Like we are getting the request for the PPTs and the course material. I request you all to please keep a check on the drive link that we have shared. In the drive link, there is one section called important announcement where all the important announcement related to the course will be given there. And also the course material will be uploaded by the end of the day as soon as we receive the presentation from the expert. Other than that, you can always use the YouTube channel, YouTube sessions for the study and reference purpose. Thank you. So good morning all, welcome back for the session. So now we have to start with the last session for today. The last session is Introduction to the Intel FPGAs and the Quartus tool flow, being presented by Israr Sheikh sir and Padmanabhan sir. Israr Sheikh sir is FAE manager Intel. He is an application engineer and manager of India, supporting the FPGA product. Israr sir also lead the customer support enablement of and co-architecture of the innovation product that target emerging FPGA usage model across the embedded telecom network, compute, and the custom design. FPGA-based hardware accelerator and heterogeneous co-processor, Edge, and AI are the recent customer-enabled programs which he is managing. He also participated in the Intel India Site Technology Office Innovation Program Startup Ecosystem Enablement Academia and Research for the FPGA and the system design. Israr sir is also a frequent speaker and the Intel and the industry event. He has over 20 years of experience in the FPGA-based system design, RTL, and the validation. He holds a bachelor's degree in electronics and communication engineering from Amravati University. We have the next speaker for today is Padmanabhan K. Sir has postgraduate degree in applied electronics from Anna University, Chennai, and he has 14 years of experience in digital design for both FPGA and ASCII. Sir is also an FPGA University Outreach Program Specialist at Intel Program Solution Group. Prior to joining Intel, he worked as a chief faculty in Sandipani School of VLSI Design, Corel Division, and he has an assistant professor and project coordinator in MSRUAS, Bangalore. So with this, we would like to invite both the speakers to please start with the session.
Thanks, ma'am, for introduction. Can I be the host for presenting? Israr here.
So we are making you the presenter.
Yeah, please.
So we have given you the presenter, right?
Yeah, I hope you can see it.
Yes, sir. We can see your screen, sir.
Yeah. You can see now full screen mode.
Yes, we are able to see.
Okay,
yes, sir,
thank you. Yeah, thanks for the introduction and opportunity here to speak on behalf of Intel for FPGA technologies. So I'll be touching about Intel FPGA portfolios, what hardware we have, silicon, as well as the software, and a little bit I will be touching on the Intel FPGA University program. Okay, so yeah, so agenda is basically to start with introduction of FPGA, then go through the portfolio and what all options are there to choose from these FPGA devices which are available. I'll introduce the latest Agilex FPGA, which is majorly like, to move, process, and store the data. Prospective, that's a data-centric world around. For sure, it can be used for the other applications, but data processing is the important one. I'll touch base and explain what are the earlier generation FPGAs, which are Stratix 10, Aria 10, Cyclone 10, Max 10 families, Quartus and software ecosystem, how it's supporting this FPGA families. FPGA based, we have accelerator cards also, which are used for the edge data center and network based workload acceleration. That also I'll touch base on Intel University program and what are the references are there. Okay, now let's try to understand and refresh. I'm assuming everyone is aware what is FPGA? Okay, but still let's refresh it, define it, and then we'll move together. What is that? You know, the gates, as we are aware, it refers to the transistors. You know, many tiny transistors are there. It is basically a piece of hardware on a chip that makes up the design. Yeah, we are aware of this. An array is means of, like, you know, there are many of them manufactured on a chip. If you see that today, billions of transistors are there. And we have one chip which is one of the biggest FPGA in the world today, Stratix 10 FPGA, which is basically for the emulation vehicle, 10.2 millions of logic element, and you very good multiply it by 10 or 12 to get the transistor number. So that kind of scale we are talking about today, how many transistors it is hosting. And field programming means, like, you know, connecting between the internal components are programmable after deployed. It means that, you know, today if I build a system and I prepare the scheme of configuration to it, tomorrow if there is a new requirement, feature changes are there, any kind of a new scheme has been implemented, deployed, that can be easily deployable into the system which is there in the field. And that all brings the programmability. That's basically FPGA can be programmed anywhere. And it means that FPGA hardwares are programmable. Let's see that, like, you know, how FPGA becomes you want it to be, like, you know, the way you want the hardware to be function, to be built based on your requirement. It is basically there are certain blocks are there, and which are the logic blocks, and other functions which are available as hardened can be brought to the configuration scheme where you are building it and you are configuring based on the need. So these are the, like, you know, FPGA blocks which are built, logic and other functions. You choose it, whether you want memory, you want SerDes, you want flops and ALU unit. Those are available. You choose and you build. How you choose is basically the way you write a program, the way you write RTL code or any kind of high-level synthesis language based code. Like, you know, you configure them, like, you know, and how it is getting connected internally, and that determines, like, you know, the functions, how FPGA performs. That has been shown here, like, you know. Now blocks used to build what you are coded is basically can be a custom state machine. It can be, like, you know, 64-bit bit shuffle and encoders are there. All together you are using the blocks which are available, is kind of a lookup table, registers, flops, memory elements, SerDes, DSPs, to building all this particular element, like, you know. So this is the block which you have coded here. And then it can be using the build using the memories or the larger memories, smaller chunk of memories which are available. You make them in a group to build large chunks of memories to store your data while processing, and then later you move out from this particular block. So even you can build the block for the math function. It can be a custom math function. A lot of DSP blocks are available here. If it is within the kind of functions which you want to realize. If not, then you can make your custom blocks also. Again, with these particular DSP blocks, you can use the configurable logic, which are the LEs, which has a flops and other IO elements to use it, included the clocking elements. Then all it's connected together, and then you can say that, like, you know, we are custom routing elements are there, which determines how your code, you take input from the one of the few of the IOs, will get in, it will get processed. When you want to store it, got stored. Processing can be digital processing, can be processing towards the arithmetic area, DSP area. Once it is done, you send it out, and that's way you decide based on the code which is available to you. So that way, all together, it is connected, and then it moves the data from in to out. And while moving a data, it process. Altogether, it's done the way you have written a code. Your code defines what kind of a hardwares we are building here in a system. This configurable system is basically the FPGAs. So now let's move what kind of FPGAs we have. Here we have a huge amounts of processing powers required. I'll talk, and then some time of you need smaller devices for your initial build-up system or powering up a system. So we have a application specific what kind of a performance you need. Those kind of FPGAs which are available. Left hand side, if you see that starting from management sensors and edge devices, which required board management or edge computing, IO expansion, or some of the automobile sensors, traffic light sensors, we have a Max 10. Then moving towards the higher workload, but still it is a very lightweight, less power it takes, towards the machine vision, embedded vision, and the robotics kind of application, increasing towards the infotainment and ADAS application. Cyclone 10 devices are there. Scalable and efficient computing performance if you need, and where you are moving towards the network side, or some people call as a fog also, or towards the data center environment where you have a workload included military and defense areas, and including infotainment and sensory or ADAS. Another applications you are adding, those devices are kind of a mid-range devices we called as a area 10 devices. Further, now we have seen in earlier talk with Jose and Demons. Moreover, they have touched base on a system which is required huge amount of computing. Today, whether it is on the edge, whether it is on the network, whether it is at your data center environment, a huge amount of data is available to us. Now, it's up to us how we are processing. For data center processing environment, where cloud, HPC domain workloads are getting processed, we have Stratix 10 FPGA, which is Intel's 14 nanometer FinFET technology. Today, what we have, Agilex, that device also has been introduced and discussed in earlier session. Today, I'll go a little bit deeper on that. That's Agilex device, which is built on 10 nanometer Intel FinFET technology, which can cater to the workload which is on the data centers, cloud service providers, accelerating various 5G wireless infrastructure, network communication, military defense area workloads. We have one more technology, what we called as eASIC. It is same as the ASIC, but it is in middle path of between the FPGAs and the ASIC, because it has very quick turnaround time, and we call it as a structure ASIC. So what happens is that, when you build a system using the FPGAs, it has a programmability, it has a configurability. On the field, when it is deployed, you can reconfigure it of a new image, new feature, new workload, required features you are building in that way. Once you are done with your development, with your all required hardware which is there built into the FPGA, you feel that let me have a mass deployment where I need to have increase the power, lesser into the increase into the processing power, lesser into the required power for the device, and we remove the configurability from the devices. We harden those routing element. We remove which are the SRAM cells are there. We harden them. Routing also hardened. That device comes, which gives the higher performance, same on the lower required power. That is the eASIC. So for some of the use cases of 5G wireless and ORAN system, we have seen that these devices are majorly deployed, as well as some of the workload on central unit CU processing within the 5G. eASIC devices are there, which are providing a huge amount of processing with lesser power, is the eASIC technology which are available. This is the little bit details of the devices which I spoken about earlier, even if you see that Cyclone 10 Max 10, even Cyclone 10 has a lesser families also we called as a LP family. We moved to Max 10, Cyclone 5, Cyclone 10, Area 10, and Agilex and Stratix 10. So if you see that on the top side, we have the low cost, less processing, but which is required for the edge analytics, and kind of a features are increasing, then we are going to mid-range as well as the higher end. Today, if you see that on the higher end, the SUD is starting from 28, which is required. It doesn't mean that it cannot cater 1G, 10G. It caters. But today, you see technology perspective, people will talk. Do we have a 25 gig Ethernet or 28 gig OTN interfaces? 50 gig Ethernet or 56 gig, 58 gig OTN interfaces, and same 100 gig pipe for the Ethernet or 112 gig of the OTN perspective. Those kind of pipe has been built, and this pipe is catered towards with the single lane, which we call as a SerDes. That technologies are there. In next generation, we are talking on the higher speed also to serve to our customer. Huge amount of memories are available here, which is embedded memory. DDR4 and DDR5 is also planned here to support on the next families within the Agilex. HBM DDR is available. PCI is one of the very important technology. PCI Gen 3, 4, and 5 technologies are very much technology which is today is very much popularly getting used to connect any of the accelerator or the devices to the main processing, which is Intel's x86 CPUs. And now we are talking by means of PCI Gen 4 and Gen 5, UPI as well as CXL interfaces. What are those? That I will be speaking more. Apart from that, hardened floating point DSP blocks are there. ARM processor, which is basically A53 in Agilex and Stratix 10 we are using, whereas in Area 10 and Cyclone 5, we are using A9 quad-core, dual-core processor for the processing element. Like, huge amount of IOs are there based on the requirement, based on the application, based on the market itself, devices, they have the number of requirements are available. So let me introduce the Agilex FPGA, which is a 10 nanometer Intel FinFET technology build FPGA. It has, as I was speaking earlier, memory coherent Intel ZPU processor attached acceleration, kind of a huge workload. If you see processing required for any kind of a co-processor, FPGAs are there today. So that's connectivity is there by means of CXL, which I'll be speaking in a later few of the slides, and which gives the huge amount of bandwidth. It is built for high performance compute as well as integration from any to any, including like the memory, analog, logic, any node. Demonstrate based on that, like these devices had built on 2.5D interconnect technology, packaging technologies, and how this is internally interconnected, why it is called as a system in packaging. I'll be speaking that in detail. And any developers, if you take today, you are RTL developer or you are the software developer, you have a means to get into these devices. Conventional flow is there, the RTL flow, as well as the oneAPI, which Jose and Divan both spoke about. oneAPI is being enabled for these devices also. So this is the FPGA. If you see that what are the elements which are available on the right hand side diagram, it's explained in detail. Main central fabric, if you see, that's a 10 nanometer Intel FinFET technology is the main fabric which hosts your all the logic here. Okay, on the left hand side and right hand side, if you see that these are the different technologies interconnected to the main fabric by means of IMEP. So this IMEP is a high bandwidth interconnect bridge technology, which is Intel. It allows to connect various technology, high fanning IOs to the fabric, so that your data transfer from that particular chiplet to the fabric, vice versa, is very high, and we are not experiencing the delay. The delay has been reduced very significantly, so that the end SerDes technology, which is basically 116 gig SerDes are there, or the CPU interface is there, which we are talking of, like by means of PCI Gen 5, CXL interface, or any other technologies, or right top of the device. If you see that high bandwidth memory cubes are available, those memory stack up are available, so those accessing are not a bottleneck. So EMIB allows us to interconnect various technologies to the fabric for data transfer, fast data transfer, high with IO buses transfer between this, so that the processing, and if you see the processing is been enhanced, and what we have achieved by means of a second generation FinFET technology architecture, that we have seen 40% higher performance on same processing on 40% lower power, and up to 40 teraflops of a DSP performance. It's very huge for the perspective of any FPGA devices. Storage has been enhanced. We have connectivity for these particular devices. DDR4 and DDR5 are also enabled on the coming series of Agilex devices. High bandwidth memory, which is basically huge stacked memories, are available, which are shown on the top of the this particular right hand side picture, is also been enabled. Apart from that, there are the persistence memories, like Intel Optane memories. Those are also enabled, are attached to these particular devices. But the way you are using DDR2, 3, 4, 5, same way you can connect by means of hardened memory controller for the Optane Intel devices also. These are the storage and processing perspective. Now, data movement perspective, 116 Gbps data transfers through a single lane of a SerDes, single lane of the IOs, is the technology has been enabled to this particular devices. First time any FPGAs are enabled with CXL technology. So that has been, I am showing here that Intel Xeon processor coherent connectivity by means of PCIe Gen 5 and CXL connectivity is coming to these devices, so that your workload, what you are hosting to the processor, and if you are sharing within the FPGA for the co-processing by means of when you are showing the connectivity, sharing the connectivity, CXL, your cache coherency accessing to the data, to the memory, to the processing element within these devices. In the software domain, it becomes a single eye view. Okay, so that way it gives you your huge processing power, and that has been enabled by means of this particular FPGA. So the data processing, storage, and data moving from in to out has become a very much faster to this particular devices by means of Intel FinFET technology 10 nanometer, as well as packaging technology, and bringing various technology to the single package, including the storage. As I was speaking earlier, we have some of the series, which series based on the series this has been enabled. Today we have F series and I series devices which host various technologies starting from from 10G, 1G to 58 gig of SerDes technology, PCI Gen 4, DDR4, quad-core ARM processor A53 in F series, enhancing that to SerDes technology of 116 gig, plus adding the PCI Gen 5 feature along with the cache coherent interface we called as the I series. And top of that, if we are adding all the storage technology, we call it as M series. So these are the series of devices which are available for the from the Agilex family. So along with that, what we are giving all together to our customer and to the researcher when you start with the FPGAs, you have an option to move to the E-ASIC, which I have spoken about, which is time to market, which gives the higher performance on the lower costing and the lower power. That also enabled from FPGA to move it to the E-ASIC. And if someone is looking that, like, I want to go to the custom ASIC, that path is also there. What I'm trying to explain here in this particular slide is that the IPs and the tools and the software which you are building for the FPGAs can be easily migrated to ASIC, and there is a path to go to the custom logic also. So it is a flexible, agile, optimized process across the product life cycle Intel is providing to the customers. This is the little bit more detail of that, which I have spoken about that. What are the tiles are there within that? What we have connectivity, we called as H tile, E tile, and F tile based on their speed, based on the hardened blocks which are there, and based on the PCI connectivity, we called as a P tile and the R tile. Important thing you see that a lot of hardened blocks are there. In F series, we see that 400 gig. EMAC, PCS, and KR, KP, RS, FEC availables are there in various configurations starting from 10 gig to 400 gig. And if you see that the power wise, how efficiently it is optimized, PCI Gen 4 and Gen 5, how it is configured, what kind of virtual IOs and CXL interfaces are there, that has been also explained here in detail. So as you see that the single lane, which we call as a SerDes, bringing you to the high connectivity to the IOs for the speed of 116 gig, and PCIe Gen 5 connectivity. Intel FPGAs has leadership today, which high bandwidth applications enabling, including 400 gig networks, edge analytics, data center kind of a workload. Of course, all the custom design which is required, these kind of features, processing, they can use these FPGAs to build their own system also included. So as I was telling, this is the first memory cache coherent accelerator for Intel Xeon scalable processor, and Agilex is the FPGA which is being connected to the Xeon by means of CXL interface, Compute Express Link. It gives the advantage of low latency, increased memory pace, and custom acceleration for various workload. It drives and accelerates various workload for the data center, analytics, AI, data analytics, and various functions as a services, so that way. And it has a memory attached both sides. So this gives a very good flexibility for the software developer, for the hardware developer, to have extended accelerator co-processing element, and which can be controlled and accessed all the resources through the software domain. Along with that, within the FPGAs, there are 4 cores are available of A53 ARM Cortex processor, which is 64-bit, which runs up to 1.4 gigahertz of processing power. And this is the hardened block, various on processing within the FPGA SoC application. If you want to build, apart from the cache coherent CXL interface with the processor independently, this ARM core processor, quad core processor can be deployed. It has a various interconnect IO elements are available. Details can be looked into that, but huge flexibilities are there within the FPGA to build your SoC. DSP is one of the leading innovation within the Intel FPGAs, and this is basically the award-winning DSP architecture what we have patented. And Agilex has the advantage of that DSP block, with additional half precision floating FP16, as well as the B float 16 processing element, which supports low precision requirements, 2 times efficiency when you're using FP16 and B float. We are seeing here from the prior generation, if you see the processing power for some of the critical workload 2 times, whereas some of the common workload we have seen 5 times increase in the processing. You can see that over 25K 18 cross 19 multipliers are there, and if you again downsize the width of this multiplier, you can see that double 50K of 9 cross 9 in a single device. So that's a element we have. It can be cascaded from 64 to make it higher configuration based on the requirement. So this is the hardened floating point DSP blocks are available for the system. So where it is suited for various workload, if we talk specifically for the AI applications, which required a huge amount of processing in terms of data representation, FP16, if you see that, it takes 40 T-flops of processing. And if you take in 8 kind of performance data, performance goes to 92 T-flops, 92 T-flops. Because of the reason that various representations are there, and your hardware has to have a flexibility to accommodate and give the efficiency. So your AI plus usage of model, it is very having a flexibility, evolving workload and multiple functions integrating for the network, ingest, security, and various data format, and it is basically it is a co-processing. So whatever the element you have, whether in the edge or the network or in the data center, you will see that this can be attached as a co-processing, and FPGA help in hosting critical workload, which required the special kind of architecture for the processing, quick processing. I have spoken about the memory, and here the details of the memories. Within the on-chip memory, we have MLAB, block RAMs are there, ES RAMs are there. Within the package, we have system in packaged HBM2 high bandwidth memory, which is having a density starting from 8 to 16 GB. That is in packaged available. Attached memory onboard, the memory prospecting DDR4, 5 are there, QDR, RLD RAMs are there, along with Intel Optane persistence memory are also can be accessed by means of a PC, by means of IOs, FPGA IOs, which is called as a memory IO hardened block. And inside there will be a controller which takes care of the connectivity perspective and controlling, managing the data transfer as well as the managing the memory devices. Security is on the topmost on any of the system. Hemant spoke about it, and to make sure independent of your system security, your device security, as well as helping towards the attach the security devices for the security perspective, we have a secure device manager, which takes care of built-in ECC memory as well as operations prior to the over fabric, which gives for secure towards the anti-tampering. It gives huge amount of encryption. Trusted zone technology has been enabled, authentication as well as preventing various malicious attacks to the system or to the FPGAs. Secure boot support is there for the private key root of trust as well as the public key only for the FPGA and the external root of trust for the devices, as well as PUF, physically unclonable feature based key technology. So those are the security environment has been enabled here. If you see that I have spoken about the second generation of HyperFlex architecture we are using within the AgileX family. First generation we have introduced into the Stratix 10. We have tweaked this to make it more faster, and why it is what is the HyperFlex, which we'll see it. But altogether, if you that faster ALM logic, faster routing, and faster clocking to give you very fast design timing closure and to get you high frequency algorithm implementing within the FPGA fabric, it allows by means of hyperflex architecture. What is this particular hyperflex architecture is been detailed here. Today on any FPGA technology other than Stratix and Agilex FPGA, if you see that flops are available into a ALM blocks, only to the ALM blocks. Now, if I have to use a flop for retyping, for retiming, for pipelining, as well as looking towards the closing the critical timing problems, for that purpose, we need the flop. If I have to get the flop, I have to go to the ALM blocks only. What we have done innovatively and differently, that we have enabled and included a flop within the routing element. You are aware that, like, you know, all ALMs and all the logic elements are connected each other by means of routing elements. So those routing elements, if we have enabled by means of registers, and these registers can be bypassable, can be enabled for your root needs. Whenever I need a flop, which is required for the retiming or pipelining or register balancing, I can use a flop along with the ALM flop, these particular flop which are available on a routing element, so that I'm not waiting for my signal to travel a good routing element delayed distance to access the flop. If I am accessing nearby flop, it means that, okay, I am reducing the delay. If I am reducing the delay, everyone know T equals to 1 by F, you know, and F equals to 1 by T. It means that I'm increasing the frequency here. So that's basically, like, you know, second generation hyperflex architecture enable us to take a design to non-hyperflex architecture 2 times. Some of the workload, some of the algorithm we have seen, it is more than gone 2 times. But easily we can implement from the non-hyperflex architecture to the hyperflex architecture 2 times. You know, so this is all together. I have spoken about the Agilex family, which is Intel's 10 nanometer FinFET technology. So we have other families also, earlier generation. Same line, we started on building the blocks around the fabric and connecting by means of EMIB from the Stratix 10. So Stratix 10 is also mainstream we are serving, which is basically a 14 nanometer fabrics are available, which has a various device families starting from GX, SX, TX, MX, and recently we have introduced NX and DX, and future devices may come into this based on the, like, you know, whether the required SerDes up to like 28 gig, and you don't need the ARM core, then the GX is the family. Within that capability, you need the ARM core SS6, the families. Within that capabilities, you need the higher amount of SerDes connectivity up to 58, 56 gig. Then we call it as a TX devices. For that, within the range, and then you need the DRAM also. That particular family and HBM access you needed, we called as a MX. For huge amount of your AI workload processing, we called as a DX, whereas the UPI connectivity, PCIe Gen 4 you require, that is a DX, whereas the AI workload and a huge kind of a processing you need from the DSP area, we call as a NX device. So these are the various devices which are available from the Stratix 10 device family variant. Earlier, I spoke about, you know, in the family plan, and we have a mid-range FPGAs, and that FPGA we called as a Area 10. It comes like, you know, SoC, non-SoC variant. It differentiate when you are taking the FPGA which has the ARM 9 processor, dual core, then it is called as SoC, non-SoC called as a FPGA, which has the GX and TX kind of a nomenclature based on the what kind of SerDes speed are there. So it gives from the earlier generation, like, you know, 20% faster performance, 3.3 Tbps of total bandwidth, up to memory DDR4. This is the first FPGA within the FPGA ecosystem mid-range as the DDR4 enabled, like, you know. So if you see that it has the lower power, 40% lower power from the earlier generation, comprehensive power feature, programmable power technology, which allows you to reduce your power further if any of the elements which it doesn't require to have on the higher frequency running, it reduces the lower time processing, including the DSP, including various DSP workload as well as the arithmetic workload, along with the ARM Core A9 processor. A huge amount of processing is available, starting from your data center, network, automotive, and IoT application. This device can cater based on your needs. Hardened block boards which are available from the Intel as well as from the partner, all for the custom build, this can be used. Next, towards the edge devices, which enables a lot of connectivity, connected system, smart, and it has to be the low power and low cost, but same time high bandwidth. We have a Cyclone 10 families. LP, one of the family which is the lower power, half of the power from earlier generation, and huge amount of like your IO connectivity it gives, whatever the limited amount of processings are there. If you see that within this particular Stratix 10 GX family, which gives bandwidth, which is improved from our earlier generation of Cyclone 5, which means of IO connectivity, SerDes, and processing. This is the device which you can look for based on the requirement what is there. For a kind of application which is required for the board management controller, literally connecting the devices and to the edge side with kind of a watt or less than watt kind of a power requirement. We have a Max 10, which is basically a first single chip FPGA, which combine like user flash, which has a Neos 2 soft core processor, which is 32-bit. Along with like dual configuration flash, analog blocks are there, DSPs are there, DDR3 interfaces are there. Bottom right side, if you see that like there's the analog hardened IPs are there, which is the 2 channels. ADC DACs are available for any kind of a sensory application. ADC DAC application using the like SAR and successive approximation kind of ADC DAC. You can use this particular device to deploy at your edge for the BSP application or any kind of initial system power up application can be used, and for the glue and for the IO expansion also. That's a Max 10 device. So now I have spoken about the hardware. Let me jump and explain you like what's the software, like it's there from Intel to use this particular devices, to bring this particular devices into the system, and to see that like these devices are easily accessible and programmable. Starting from the left hand side, if you see that like we have a Quartus tool, Prime Pro and standard suits editions are there. Those are like conventional flow. If you want to use it, you are the RTL engineer, VHDL Verilog, and you know how to code it and how to get best out of the resource and the algorithmic performances. You'll go for the RTL implementation. We call it as a bare metal also sometime. But if you feel that like let me go towards the higher end side, you move towards the kind of a high level designer backend compilers, like then you move to the DSP block, and HLS is the where you intercept to the next technology, where like OpenCL and other C kind of algorithms you can bring in. High level synthesis using compilers is been deployed to bring into the algorithm which are non-RTL. OpenCL or C++ also, it's not mentioned here, can also be used here. Further, if you want to go and the software domain, parallel compilers are there, which includes like OpenCL and other, as well as like deep learning accelerator. And if you go to the software stack, is basically like, you have a tensor flow kind of flows are also enabled here. And then you can go towards the stack level and the library and primitive level development. So altogether, like, am I a hardware developer? Am I a software developer? What is my priorities to build quick system, or you want to have a robust performance, or you want to look for the productivity, and based on the requirement, based on the expertise, based on the people, those who have the capabilities, we can choose starting from the hardware developer RTL towards the HLS compilers, towards the software domain, which is basically stacks and the software building for the FPGAs. We have heard from the earlier session, Jose and Dhiman, they have touched base, like, what is the overlays, how it works. You build system once, deploy it, and by means of software stack, which has built a system around to make sure, like, from the software domain, from the very high level domain, you are reconfiguring the FPGAs, which is there deployed, and for the various workload. That's one thing. And oneAPI is the one of the way also we have heard about that, is basically how we are enabling this is a special architecture along with Intel CPU, Intel GPU, Intel's AI chip. FPGAs are also enabled to make sure, like, on a combined and the software domain, which is the one window for the software developer to access it and get the workload based on the requirement of hardware. It is being targeted, and FPGA is one among them. That's a oneAPI technology. So altogether, this is removing barriers for the adoption. Any ecosystem perspective, how to deploy, how to include into your flow. Intel is committed, build, continue to do the innovation towards the software to support the silicon which are available, like, and with that, Intel is not only a silicon vendor, it is a building boards, and it builds the systems also. We have ecosystem partners. Sometimes boards comes from us, sometimes it comes from our ecosystem partners. If you see that FPGA based board, which is basically from left hand side, if you see that it's for the embedded and the edge application, which is basically required real-time actionable intelligence at the edge. FPGAs has the board by means of OpenVINO and next generation technology, which we are called as a core DLA, which is available today for with the early access. Maybe in 6 to 8 months down the timeline, it will be released. That's a core DLA, also available for the edge analytics for your vision workload application. Middle portion, if you see that communication infrastructure, which is high bandwidth aggregation and processing, we have here we have N3000 and N6000 kind of devices, which is very much popularly used for all 5G application. You can see that you can search it, N3000 deployment story. You can see that various customers, they have publicly announced it. Rakuten is one among them. How their enterprise network has been deployed, accelerated various critical function, which is LDPC, fact acceleration, or other kind of L1 layer network workload. And parallel processing has been enabled using the N3000. N6000 is the next generation is there. For the cloud and enterprise perspective, if you see that various workload for the data acceleration perspective, Rush Creek is there, as well as D5005 card is there. Recently, we have announced SmartNIC, which can fit both sides, where the communication infrastructure as well as the cloud and enterprise infrastructure. It has it has a Xeon D core also within the card, so that you're not burdening your core processor. You are on the PCI connectivity Gen 4, Gen 3 perspective. You are various workload you are accelerating using this particular card. that way. Let me touch base on Intel FPGA University program. Dimant has also spoken about that. It has a 4 major pillars to enable this particular program. We definitely want everyone, researchers, everyone which are there connected to the academia, or those individually they are there as a professional into the industry. We want enable them whatever we can help to learn them, to learn, to research it, bring new innovation, new kind of a implementation, or new kind of a processing, and you kind of a managing the data, or what's the futuristic technology you want to prove it. That's another pillar. We have a research. Along with that, we want to enable our academia professors to teach these new technology to the people, those who are there and using this, and then develop it along with the ecosystem, startup companies, or your own ecosystem, how you want to develop it. That's another thing which we are enabling our partners. Academia and researchers are at the forefront on this, by means of FPGA University program. We have designed very university focused curriculum and content, which goes like semester long lab exercises for hands-on learning with suitable with solutions which are available. Tutorials are there, online workshops, self-study, and the key use cases are available. Free libraries and for the IP and common for the student projects has been enabled. Example designs and sample designs are available for our professors to take up to the class, and students to take advantage, researchers to continue and expand their research on this domain by using this infrastructure is been enabled to our researcher and academia community. This is the most of the widely used software which are freely available. This is a very powerful tool for the RTL implementation. And if you see that, which is basically a Quartus, EOS is the processor, along with that, Model Sim is the simulation tool, FPGA SDK for OpenCL, which is basically with all our boards which I have spoken. If you want to take access or you want to deploy on your customer custom boards, OpenCL Flow SDK is also been enabled for the customer. For your edge vision and edge analytics, deep learning accelerator suites are also available for. So this reference is given on bottom, and we will be speaking, and we have shared also by means of prerequisite. This can be accessed to all our participants, and it will be continued to you to access for your future work within your lab or for the practical or the classroom classes purposes. Along with that, these are the popular hardware which are most of the universities which are allied with us is been enabled to them. To most of the universities we have enabled here. IIT Guwahati is one among them, where we have situated Center of Excellence. Various boards of these form factors are available, and these are the basically starter versions of the boards are there. Prices are very much written here. Very lesser price boards are there under university program. Few of the boards we can enable along with the software free of cost. Also, there are certain criteria are there which we have to meet. But these are the board which are the students and to build the maker project and to develop it, demonstrate it within your lab. And this board can be accessed virtually also. In the next session, Padmanabhan will speak about that. Is available to you. Get in touch with us. You would be speaking one more session in next coming days. What are the various labs has been built around this particular board along with the other boards to take the advantage and take up the innovation to the next level. So total access to all the developer whatever resources are there has been given to innovate towards the your academia research or next generation research, All documentation, design example, support community, virtual on-demand training and references are available here to take advantage. This is some of the courses which are available to the starter side for the university program, starting from digital logic to the computer organization, embedded system, and AI side. So these are the starter labs and the courses are available. And next to that, like, you know, domain specific crash courses also has been built, which can take to the core teaching, and that can be a credit kind of a courses, specifically if you are looking for, like, you know, a huge amount of data processing, HPC domain, AI, machine learning, deep learning, as well as communication, EW, radar, area communication, secure communication, and ADC DAC kind of devices interface. A lot of credit course has been built, and which we would be sharing in next sessions or maybe coming days for you to take advantage of these courses. Many more options are there. Let us know how we can collaborate and take the innovation to the next level and strengthen and build our academia and research independent, so that you people are independently executing it, and there is innovation is inculcating starting from your starting semester 1, semester 2 areas. You know, some of the training online references are there, which we have shared earlier also. For your reference, I have brought in to get you a reminder that, like, you know, you go and search, like, you know, on Intel site or into the any kind of a search engine Google, that Intel FPGA trainings, you know, you will find a lot of trainings. Those are freely accessible. Register yourself, get advantage of those training, which are you can access anytime on your free time, so that what innovation you want to bring in, you are learning it before you are coming to the lab, before you are coming to the innovation, before you are building a system, so that you are fully aware of this, starting from the basic lecture, basic architecture of FPGAs, how to take a VHDL Verilog, like, you know, Quartus implementation, like, you know, what are the various tools are there, those has been enabled for you to take advantage of this, like, you know, and how to take up the SOC systems and to build you know, parallel computing using the OpenCL. These are the some of the points and has been highlighted here, but you have a huge amount of trainings which are available, freely available. You can access it, update yourself, get knowledge, and bring the innovation to your course site as well as the research site. So here I'll stop my session. If you have any question, I can take up. Otherwise, Padmavanavan will take up the next session here. Okay. Any question for me?
Hello, Israr. Israr sir, I think there is a question in Q&A.
Yeah.
By just a second, let me see. Question is asked by K. Bapaya. What are the various developing languages we can work with FPGAs? Can we enable operating system on FPGA like Xilinx, microkernel, etc.?
So we have, as I was speaking, like, you know, the base language everyone use VHDL and Verilog for simulation perspective, including, like, you know, your ways of simulators are there that are being enabled, and system Verilog is enabled for the simulation perspective. For the implementation perspective, we can see the OpenCL, HLS by means of C, C++ languages are there to enable, and by means of oneAPI, we can use any kind of algorithm which is there in the software domain to access the FPGAs. So that's something various kind of means to get in realize your ideas to the hardware, is being enabled.
Hello.
Yes.
Hello, Mr. Sheikh. Thank you very much for your excellent information regarding the Intel's product. I'm a Professor Kondekar from IIIT Jabalpur. So under your university program, there are plenty of opportunities for our students. So I would like to know more about what infrastructure facilities Intel will be supporting for an institute of national importance if we collaborate with Intel and would like to extend these type of things to our students.
Good question, and yeah, good vision. I can hear from your question. Thanks. Yeah, before I go to your question, I think from earlier question I missed to answer. So basically, on the software perspective, we have a huge amount of ecosystem for the ARM core processor, starting from like any kind of OS, Linux or micro Linux, Windows kind of OS. Various OS can also be enabled using the SoC ARM architecture. Okay, and we have a NIOS core also, 32-bit soft core processor that can also be utilized. It also enables various OS to the FPGA to build the SoC. Yeah. So now coming, Praveen sir, to your question, we have a various program to get collaborated with the institute and researcher community to take up their vision to the next level. As I have explained in my talk, we have a starter board, which is basically using the Max 10 Cyclone 5 SoC and non-SoC variant boards are available. And in earlier slide, I have spoken about Intel has built-in cards are available also, which is for the edge analytics network as well as the data center area. So we have various these kind of hardware along with that Intel processing element, which are the processor and the GPUs. Specifically, from the FPGA perspective, those boards can be utilized for your vision and mission to get collaborated. And whatever ways Intel can help, we will extend that to enable those whatever the software and available firmwares are there, along with the IPs that can also be extended. So that's on the top level. Maybe specific to go on that, we can speak more and based on your requirement, what else can be brought in, we can think over that.
Right, sir. I think even we want to know how to initiate the things in that direction.
Exactly. So to myself or to Padmanabhan, you can write, and we will take up this to the next level.
Sure. On a technical side, I just would like to know if an FPGA, which is of high end, is underutilized for some application in academic point of view, because in academics, final application is not well defined or well. So in that case, it is an underutilization of that. So whether a low end start will be okay or a high end FPGA will be good to use.
I think, so this is basically towards the kind of a workload what we are looking to get realized.
Right.
To start with that, mid-range, I would say that, would be a good one, which is basically
because time to time there is a upgradation required in case of academics. It will be
exactly. Yeah. So we have enabled both kind of boards to the academia, starting from starter to mid-range to the higher end. And RTL is RTL. Today I can write small piece can be realized on the smaller board. And tomorrow, if I go and that is, I'm expanding by adding a lot of features, can go to the mid-range as well as to the higher end also. But that way it works, what kind of RTL I have. Yes, good question.
Thank you. Yeah, thanks a lot, sir.
Yeah.
We'll write to you soon.
Sure, sir. Yeah.
Okay.
Yeah. Further, if any questions are there, I'll be more than happy to answer. I'll be here in this session further. If no questions, let Padmanabhan take up to the next session. Adi?
Yes, I am sharing the screen now.
Yeah, thank you, Israr sir, for your wonderful talk. I think Padmanabhan sir, we can start.
Right, you are able to see my screen?
Yes, yes, your screen is visible.
Yeah. So good afternoon, everyone. Welcome to the Quartus Prime Design Software Tool Flow. So before getting into the details of the Quartus Prime Design Software Tool Flow, so I need to just show you where you can download the material. Okay, that means you can see. You can go to Download Center for FPGAs. You're able to see here. You go to Download Center for FPGAs. You can see here select by device and select by version is there. So select by version, you can take 20.1. So this is the version we are going to use. And then you could be able to see there are three editions here. One is the Pro edition, and then you have the standard edition, and then we have the light edition. We are recommending you to download the light edition because it supports the Cyclone 5 devices as well as the Max 10 devices, which we are going to use for the lab day and then for the SOC programming. So the standard edition will support the ARIA 10, then Stratix 5 devices. You could be able to see, and what we Isar has discussed in the earlier session. And then you could be able to see Pro edition. It supports Agilex, Stratix, ARIA, and then Cyclone 10 GX. You could be able to see the newer FPGAs are getting supported in the Pro edition. So what we recommend you is to install the 20.1 Lite edition. You could be able to see that this Lite edition, when you say download, you could be able to see that you can download either in the Windows or in the Linux version. You could be able to see Quartus Select Edition Lite and say 20.1. And then you could be able to see the combined files where you could be able to see all the informations are available here. What is included is provided here. Quartus Prime Lite Edition, Model Sim Intel FPGA Starter Edition is included. And then you have the device support. You could be able to see the Cyclone 5 as well as the Max 10. And for the SOC session, we recommend you to download the standard edition 20.1. And in the additional software, you can download the Intel SOC FPGA Embedded Development Suite Standard Edition. So this does not require a license. We are recommending you to download this. Okay, right. So let us get into the session right now. As I explained to you earlier, the Quartus Prime software has three editions. You have the Lite edition, which we call that as LE, Standard edition, which is SE, and then you have a Pro edition, which is PE. This is the information which I showed you earlier. You could able to see the Pro edition, Standard edition, and the Lite edition, and what is the supported devices is provided here. So the Standard edition and the Pro edition requires license, whereas the Lite edition does not require a license. So no license file required for the Lite edition, whereas the Standard edition require a license, which we call that as a subscription edition license. Will work with the Standard edition, and then the Pro edition require a new feature license file again. And what we are going to use for our demo and for the courses is for the Max 10 and Cyclone 5 device support. It is recommended to download the Lite edition. And what we are going to see demo today is also based on Max 10. So Quartus Lite edition is sufficient. What is the Intel Quartus Prime design software? It is a fully integrated development tool. It has multiple design entry methods. So you can use VHDL, you can use Verilog, and you can also use System Verilog HDVL, so which is a hardware description and a verification language. So it performs logic synthesis, place and route, as well as the device programming. We knew that logic synthesis means we are going to convert the RTL into a gate level schematic. That means you are going to translate into a gate level netlist. We knew that there are three important characteristics in an HDL. The number one, simulation. Number two, synthesis. And number three, documentation. That means you could be able to ensure that we should perform simulation. That means you are going to get the functionality by passing valid test vectors to the design. So in our Quartus, it includes the Model Sim Intel FPGA Starter Edition, where we can perform functional simulation. And then you can perform synthesis. And then you can also perform control. So after performing synthesis, there is another characteristic in HDL called as documentation. That means either you can follow bottom to top approach or top to bottom approach. To get into the details, you could able to see what is the operating system support. It supports 64-bit Windows as well as the Linux support. And we are going to create a new project wizard. As I explained you that you could use either VHDL, Verilog as well as system Verilog. And there are different constraints you need to apply. There are pin constraints and then there are timing constraints. So today we will focus on the pin constraints, and then in the later sessions by tomorrow we will be learning how to apply timing constraints in the timing analysis session. Right. So let us get into the understanding of how to open the tool and what are the informations that need to be taken care of. So just you could able to see Intel Quartus Prime development suite. It opens here. You could able to see there is a new project wizard, and then there is an open project. How we are going to create a new project? When we are going to create a new project, we have to new project wizard. Let us start with a very small example first, and then we will move on to other side of examples, and then we can also see how those boards can be accessed remotely. Now, when we start with a new project, what we need to understand is also, which is very critical and important, is we need to know which board we are targeting. For example, I say the Max 10 device, which is the DE10 Lite. This is the manual. So Terasic is our partner, so we can download this lab manual, and then we can see what is the device information and what is the family information. Those informations we can get from this particular logic. Let me open it. So you could able to see this is the DE10 Lite user manual, where you could able to see that what are the package contents and what is the thing we are going to see is based on the DE10 Lite board. And what we also need to understand that what does it consists of. You could able to see that it has 10 LEDs and then 10 switch buttons as well as the 6 hexadecimal displays. And what is the device name you could able to see here? This is 10M50. That means it has 50K logic elements. So when you are creating a new project, we should know how are we going to filter the specific device. Let us go back to the Quartus Prime Lite Edition window. You could able to see there is a project navigator window. You could able to see the tasks where you can see the compilation. It performs analysis and synthesis. That means it performs elaboration first, and then it performs synthesis, and then it performs a filter, which is called as placement and routing. And then it generates the programming file where we call that as an SRAM object file, which is a .sof file. And you could able to see the IP catalog where you can get all the intellectual properties like RAM, ROM, FIFO, and then all other Ethernet and PCI Express controllers in the intellectual property blocks. Knew that an IP is pre-designed, tested, and then pre-verified. So let us start with this. I click the new project wizard here. The moment I click the new project wizard, it shows the new project wizard helps you to create a new project, and then it generates the project settings, including the following. You have project name and directory. You have the name of the top level design entity, project files and libraries, and the target device family and device, and then you are going to do the EDA tool settings. So since we are going to create a new project, we need to provide a project name, and then we need to provide the name of the top level design entity, and then project files and libraries, and then the target device family. So since we are going to target the device family, which is Max 10, we have to understand that how do we filter the specific family. I say next here. You could able to see what is the working directory for this project. So just I start here, C, and then I say FDP program, something like that we can take. And what is the name of this project? Let us take a small example. I start with a small logic gate. I say here C drive, I gave FDP, and then I gave what is the name of the project. I have provided the name of the project, the top level entity name. So you could say next here. It is asking that the FTP program does not exist. Do you want to create it? Yes, you can say yes, you create a new file. Now we'll say empty project. What is the basic dot? There is a project template. The project template will have all the information already available for you. But since we are very new to the Quartus, it is recommended to start with the empty project. You could able to see choose a new project specifying the project files and libraries, target device family and device, and then the EDA tool settings. So the EDA tool settings will help you. What is the simulation tool, the model sim, Intel FPGA starter edition, how are we going to use it? How are we going to perform the task? That informations we can get in detail. I say next here. So I'm not going to add the files because we are going to create a new file. So you could able to see that the select the design files you wanted to include in the project, they are already available. Since we are going to create something new, then we don't want to do this section. You can just skip and go to the next here. So this is a very important logic for you. What is the device family we are going to target today is Max 10, which is the low-end device. You could able to see that the Max 10 DA, DF, DC, CA, and SC. We need to filter it. Filter that I showed you in the DE10 Lite lab manual. What is the name of the filter? You could able to see that 10M50 because it is having 50K logic elements, right? And say DAF, and then I say 484. That is the name of the device. The moment I provide this information, you could able to see okay what device you can select. Okay? And then you can select the device specifically so that you could able to see here. Right, so DAF 484, then you could able to see C7G devices there, so that you can able to see, for example, C, then you can see 7. Right? So the device you can select here, specific device, and then say next. So in the EDA tool settings, we are not going to set anything right now because I'm going to use the model sim Intel FPGA starter edition, right? So we can set it later. Just say next. Now you can see the summary page here. It shows the project directory, right? And then you could able to see C drive, FTP, and the project name, the top level design entity, and then you could able to see the family name, what it is provided, and then the device, and say finish. So now we can wait till the Quartus opens the Prime project and the design. Right. As I explained you that we are going to create a new file. So you can go here, file, and then say new. Could able to see that as I explained you earlier, it supports VHDL, Verilog, as well as system Verilog. We are going to write a piece of Verilog code. So I can select here Verilog HDL file. And then I say OK. Okay. Now, the moment I select the Verilog HDL file, you could able to see on the top, it shows verilog1.v. We are going to save that as a different, because what is the name of the entity we know, we have to save it accordingly. I say here module, and then what is the name of the file is, and get, I say now, I can write input A, then B, and I can write output Y. Then we can say assign Y is equal to A and then B. And say so we have developed a small piece of Verilog code. You need to save this right now. So once you develop a small piece of RTL, you can save here like this. So file, save as, then you can able to see here and underscore get.v, then save. Okay, so once the file is saved, now what we are supposed to do, we need to perform analysis and elaboration. So when we do analysis and elaboration, it is going to check for the syntax errors, and then it is also going to perform the initial synthesis for us, where we can refer the RTL schematic of the given RTL. Let us perform that. You could able to see next to the play button compilation, you could able to see it shows start analysis and elaboration. You could able to click that. right? The moment you start analysis and elaboration, you could able to see the design starts elaborating, right? And it shows 100% right now. That means the design is elaborated without any errors. That means you could able to see here Quartus Prime analysis and elaboration was successful. And it shows 0 errors and then 1. Now we need to check whether the code what we have written is providing you the exact schematic what you have done. So what I told you, what are the different characteristics you have to perform simulation, and also you need to perform synthesis. So in this case, we need to understand that whether it is providing the correct hardware or the code. For example, you could be able to see here tools, and then you can go to netlist viewers, and then you can go to the RTL viewer. The moment you give this RTL viewer, now you could be able to see that A and B are the inputs, and then it provides Y as the output. So now you could be able to see that, okay, the code what you have written is providing you the gate level netlist. So what is very important for us right now is we also need to develop a small test bench, and then we should verify the functionality. That is critically very important, because when it provides the correct functionality, then it is easy for us to proceed to the synthesis stage, and then we can perform planning, and then we can generate the SRAM object file, and then we can program that onto the board. So before getting into the details one by one, we will understand the process, what is happening in the Quartus tool flow. So we have developed a small Verilog code, and then we have performed analysis and elaboration, and then we have experimented that and checked whether the RTL schematic is fine. Now let us develop a small test bench for this code, and then we can integrate that with the Intel FPGA Starter Edition model sim, and then see what is the specific feature. Then you go back, file, and then say new, and then you have to again say Verilog HDL file. So you have to go back to file, and then say Verilog HDL file, and then say OK. Now you could be able to see that it has opened one more space for you where you can type the Verilog code. So I'm going to develop the test bench. You all knew that a test bench is a top level module without any inputs and outputs. And you know that there are 5 components in a test bench. One is the data type declaration. The second one is called module instantiation. And the third one is called as procedural block declaration. And fourth one is called as the test case generation. That means you need to pass the valid test cases. And the fifth one is called as the display statements, where we can provide the outputs. That means you can display the inputs and the outputs, right? Now the inputs are converted into reg. So I say reg AB, and then I say wire, then Y. Now I need to write the module instantiation. So I say here add underscore gate, and I say A1, and say dot A is connected to A, and then say dot B is connected to B. And then I say dot Y is connected to Y. So we have done data type declaration as well as module instantiation. Now we can develop the procedural block declaration. So procedural block, we have 2 in Verilog. One is called initial, the other one is called always block. So we use initial block in the test bench. I say here initial begin. Then what are the initial values? I say here A is equal to 0, and then B is equal to 0. And I can just write after 5 time units, I wanted to change the value. A is equal to 0, and then I can say B is equal to 1. And then again after 5 time units, I say A equal to 1, and then I say B equal to 0. Then again after 5 time units, I say A is equal to 1, and then I say B equal to 1. I say end, and I say initial, then we'll say $monitor, because monitor will continuously monitor if there is a change in the value of the variable. So I write $monitor, $time, then we'll say what is the value of A. So A equal to %B, and I say B is equal to %B, and I say Y is equal to %B, and I say A then B, then what? We need all the three. So I will say end module. I need to save this file. So you save file and then you can say go back save as and say and underscore gate underscore tb dot b. You can save this file right now. Now need to also check whether the design functionality is proper by enabling this test bench. So first we will perform the settings properly, and then we can perform analysis and elaboration, and then we can also check the logic. So first we'll perform analysis and elaboration and then check is there any issue with the design and the test bench. So now it shows 100%. Now what we have to do is you have to go to the assignments, then go to the settings. So please see the steps very carefully. Go to the assignments and then we go to the settings. And then we go here simulation. And then here full name shows none. So this has to be changed to model sim, which is our FPGA starter edition. And we are going to compile the test bench. That means it is asking what is the name of the test bench. You can click here, compile test bench. And then you can go to the right hand side and click here test benches. And then we click here new. The moment you click here new, it is asking what is the test bench name. Now what we are providing here and underscore gate underscore t. What I have provided the test bench name and underscore gate underscore tb. Now I need to add this bench, which is available in the directory where I have created the file. You can click these three dots. It will open here and you could able to see and underscore gate underscore tb dot v. Just click that and see open. You click add, and automatically this will be added. And then you could see OK here. Then click OK for this tab. Apply. Then you click OK for this also. So remember the settings. You have to go to assignments, then go to settings and cross verify whether model sim alter is select. Simulation model sim is provided and your test bench is set already. Okay, your test bench is set already. Next time you don't want to set it again, you can automatically run the simulation. Now we are doing this for the first time. We have to set it right now. How are we going to perform simulation now? Go to tools here and say run simulation tool and then RTL simulation. So remember the step once again, you have tools, run simulation tool and then RTL simulation. You could able to see the model sim opens and you could able to see the output. Okay, so now you can open the model sim tool here. It shows now Intel FPGA Lite edition, which is the starter edition. You could able to see that. You could able to see the outputs here. When A is 0, B is 0, A is 0. When A is 0 and B is 1, Y is 0. Then when both are 1, that is Y equal to 1, B equal to 0, Y is 0. When both are 1, you could able to see the output is 1. And you can check that in the performance. Able to see when both are 1, you could able to see the Y is 1. So what we have done so far is we have developed a piece of Verilog code. And then we have developed a small test bench for that. And then we performed a functional simulation also for that using the model sim. You want to close this window separately? Yes, you can. It's asking, are you sure you want to? So since we have checked the functionality, you can say yes for this. I close this window right now. And then we are again coming back to the Quartus. Right. So now we'll take a break here and then we will enter into the slides and understand that whatever steps we have done so far, they are available there in the session logic. could able to see there are different analysis, and tomorrow we are going to work on static timing analysis, and then you could able to see on the simulation, you can able to see the model sim Intel FPGA starter edition is enabled for you. So welcome to the Intel Quartus Prime design software. This is the window which I showed you. We created a new project wizard, and then there's an open project. Means I need to show you one example of opening the project. I will show you that also. Now, when we created a new project wizard, we created the project, and then you could able to see there is a project navigator. There is a tasks window which explains you about all the tasks which are available for compilation, which performs analysis and elaboration, synthesis, filter, which is called as placement and routing, and it generates the programming file. And then you can have the tool view window where we have developed Verilog code, and then there was an IP catalog which explains you what are the intellectual properties that are available, and then followed by the message window. If you want, we can enable the kill window in order to apply the pin constraints to the design for creating a project. This is the main toolbar which is available, and then you could able to see there are different menus that are available. One is the file control, then dynamic menus, you have pin planner, you have chip planner, you have the compilation controls, and then you have compilation report, platform designer, and the IP catalog, timing analyzer, interface planner, and book. So most of these things would be described to you during our course. You would be learning timing analysis, you will be learning programming, you will be learning IP catalog, and then you will be learning platform designer, and then you will be verifying the compilation report to see that what are the resources that are used. Right? Let us go back to the tool once again. We have stopped with analysis and elaboration. Let us see what are the processes that are available in the compilation. You could able to see that on the left hand side, it shows the tasks. And then you could able to see on the right hand side, what is the time taken for each and every task is there. So right now, what we are supposed to do, we can perform compilation. So what does that compilation process involves? The compilation process involves, you have performed the analysis and elaboration. That includes the initial synthesis. Then it performs synthesis, where you are going to convert into technology mapped, right? So one is called the post mapping, the other one is called as the post fitting, which is the post routing. So we are able to see all the three schematics right now. Let us start the process right now and then perform compilation. So this is the play button for compilation. Just watch carefully. I say start compilation. Could able to see what are the processes that are happening. Running Quartus Prime analysis and synthesis. Then we are going to generate the programming file till now. And what are the different kind of netlist viewers that are available with this process? We can get into the details right now. Okay. So now you could able to see earlier it was not showing the exact details. Now you could able to see how many number of logic elements are utilized and how many number of registers are used, because it's a very small combinational logic block. You don't require any registers here. It shows 0. And you could able to see the total number of PLLs, ADC blocks, what and all has been utilized, that is shown in the compilation report. Now again, we can go back to the tools. Then now you can able to see the netlist viewers. The netlist viewers, earlier we have seen only the RTL viewer. Now you could able to see technology map viewer, and then technology map viewer, that is after post fitting, and then you can also see the state machine viewer. I will show you state machine viewer with another example, but then we can see the post mapping, which is the technology map viewer right now. So you can click the technology map viewer. You could able to see that everything is shown in terms of lookup tables. You can able to see the logical cell, which is a combinational logic block. You can able to see the input buffers A and then B and then the output. Similarly, when you perform the same operation with the technology map viewer, which is post fitting, you could able to see that it uses all the combinational blocks. You could able to see that it shows A, B, and then Y, which is a logic cell. can able to see what are the basic elements that is used by the design. So you could able to see what happens during the synthesis and then the fitting operation. So we will get into the details into the slide later. But then now what we have done so far, we have performed the compilation. When you perform compilation, it performs synthesis for us, and then it performs the placement and routing, which is the filter operation. Right. Now, finally, what I can also show you, I have shown a small design right now. Let us open another design, which is a small counter project. I just open the open project. The earlier case, I just created a new project. So I'm just opening a new project. We're able to see that I wanted to open a project, and then I need to show the small example for you. Let's take this example. There is a counter simulation project. Just open that QPF. So QPF stands for the Quartus project file. You have already created a project. You can able to see there is a file called QPF. I'm just opening that Quartus Prime project file now. So we are going to understand all these things right now. So you have opened a project. That means you could able to see the files which are available in that project. In this place, instead of hierarchy, to expand that files, then you could able to see there is a count.v. There is a file which is a 4-bit counter. You could able to see that. And then there is a counter underscore tv.v. There is a test bench that is also written. So what we are supposed to see here is the example. What we have seen is a pure combinational logic block earlier, which does not show any registers for you. But this in this example, you can see the different schematic where you have a combinational logic block between the registers. I will show that along with the simulation. So what is the basic thought process? I compile this design for you. You could able to see the target device is still max 10 device. Okay. And again, you can revisit the test bench, what I have discussed in the earlier case. What is the only difference is we have developed a free running clock here. Okay, so let the compilation succeed. Right, so you could able to see 100% here. Since already the test bench is set, you can go here, run simulation tool, and say I here RTL simulation. Since the code is already written, I just wanted to show you the simulation perspective of what happens when the design is a counter. Okay. Right, so I just break design here, and then you could be able to see the counter is. So you could be able to see that. Right. So you could be able to see the counter counting here 0001, 0010, 11. You'll be able to see, and then the moment it reaches 1111, it is resetting and then starting the count. All right. So we have seen two examples. So one example is a pure combinational block. The other one is a counter. What is the intention to show this is to see the different netlist view. Okay. So I need to show here the netlist viewer, which is an RTL viewer, which you could be able to see the adder, that is your incrementer, along with the counter. You can able to see 3 down to 0. That means there are 4 flip-flops it is going to show you. You could able to see in the netlist viewers and in the technology map viewer fitting. Could able to see there is a register, and then there is a combinational logic block, and then there is a register, then combinational logic block, register, then there is a combinational logic block, and then register. You could able to see that. And in the compilation report, you could be able to see in the report view, you could able to see that what is the resources that is used. To get able to see that the total number of registers it shows. And you could able to see that in the earlier case it was not showing that, because it is showing register 0 because it's a pure combinational logic block, but then it shows the number of registers 4. Okay, so let me keep this design aside, and then we will enter into the AND gate design. We have done synthesis, and then we have done the filter operation here. Now what is the next step? We need to implement the design onto the board. Then we need to implement the design onto the board, which is very important. What aspect we have not done is called as the pin planning section. Now, when we enter into the Quartus flow very carefully, we are able to understand that. So we have all the options, and then click the empty project, and then you could able to see either VHDL or Verilog or System Verilog you can choose. Then you can provide the family name, and then I told you what is the field you need to apply. And then we have given the EDA tool settings here. I told you you can select your model sim, or you can set it after you enter into the project. And then you can be able to see the summary. So this is a step one by one I showed you during the tool. All these things are captured in the slide for your reference to refer later. And then, as I explained to you earlier, when you are opening a project, you can open from the file menu, or you can say recent projects would be highlighted in the home screen, or else if you wanted to open a project which is already available, you have to double click the PDF file, which is called as the Quartus project file. So all these things are shown to you. In the first example, we created a new project. The second one, the counter which I opened and then shown the simulation for you. I opened the project in which the QPF file is already there. I just opened the Quartus Prime project file. Right. Now let us enter into the design, and then we'll understand that how are we going to perform pin planning for this design. Now go back to the FPGA device. As I explained to you earlier, you could be able to see there are 10 switches, and then there are 10 LEDs that are available, along with the 6 hexadecimal displays I told you for the DE10 light port. So before programming, what are the steps we need to do is we need to configure the pins properly. So we will enter into that portion right now. Let's start from here. So it has a 50 megahertz clock. The clock pin is pin underscore P11. And then you could able to see that what are the push buttons. There are 2 push buttons you have, and then you have 10 slide switches, right? And then you have 10 LEDs. Right. What is very important for us is what are the switches we are going to use for the inputs, SW0 and then SW1. There are 2 switches, which are the slide switches. You could be able to see the pin configurations here, pin C10 and then pin C11. And what are the user-defined LEDs we have? We have LED R0, which is a pin A8. Okay, so we require only 2 switches and then 1 LED for this design, for this small AND gate. And what is the voltage we are applying here is 3.3 volt LVTTL. And here also you should see it is 3.3 volt LVTTL. How are we going to perform pin planning in this case? Right. So let us assume that we require only these 2, that the pin C10 and pin C11 we will take. And then here we will take the LED R0, which is pin A8. Let us open the design. How are we going to perform pin plan? You could able to see here processing. You can click here, okay? And then you can able to see the what are the different processing which I can show you. You can able to see the compilation report, synthesis report here. Similarly, when you go to the assignments, you could able to see that pin planner. You can just click that. When you click the pin planner, it shows that 10 X10 device, which is a 10M50 DIF484. And now we need to enter the pin correctly. You could be able to see that A is an input, B is an input, and Y is an output. It is asking for the location. Okay. Right. So now A is an input, B is an input, and then Y is an output. It is asking for the location, means we are going to specify the location in the location box here. So let us again configure from here. The pin C10 we are going to use for SW0, and the pin C11 we are going to use for SW1. So we can enter that here. I can say pin underscore C10. This I am going to use here. Then what I also need to do is it is a 3.3 volt LVTTL, so I have to select that. And then the other one is pin P11, so which I need to use. Along with that, I can also change the voltage here. So pin C10 and pin C11 we have provided. But what we are supposed to do for LED 0 is pin A8. So pin underscore A8 is the location. So we will do that. Pin underscore A8 is the location. So you have provided that. And then you could able to go to the voltage again and then specify 3.3 volt LVTTL. Cross verify here whether that is right. And then you can go back to the design once again. Okay, so when we do pin planning in this case, you could able to see that all these values are specified. Now we can go to the design. Okay. So now the moment you open this design, you could able to see that we have done the elaboration. Now we can form the compilation and then see, because since we have modified the pin planning, it is recommended to perform synthesis and placement and routing once again. So I press the compilation button once again, and then we will perform that. So see the steps very carefully. Earlier we did synthesis and then we do placement and routing, but then we tried to change the pin planning. We are again need to do. So what is the step? While performing the synthesis, it is better that if you are very clear that what is the planning that could be done, that can be processed. Okay, now you could able to see the total number of logic elements and what is the device that is specified. Now you could able to see the design completes with 100% and it generates the programming file. So where that programming file would be located? The programming file would be located in the output files directly, okay, which is called as a SRAM object file, which is a .sof file. You could able to see that it is generating that assembler, which is a generate programming files. For each and step, for every step, what is the time taken is also specified. Right. So now I have connected the board with me right now, so that I could program the design, and then I could able to change the switches, and then I could able to see whether you are able to see whether Y is 1 or 0. Okay, that we will check it first. Then the second principle what we are going to change and what we are going to understand is in the challenging period now, how are we going to access the board virtually, which we call that as a remote console. Okay, we will understand that process, which would be very interesting for you, because now we don't have the board, but then you wanted to see the GUI of the board in the screen. It would be helpful for you to understand what is the basic process for it. So let us start with this right now. Now I need to program the design. So how do you program? You have to go to tools, and then you should go to programmer. So click tools, and then you can go to programmer. Now you could able to see that what is the name of the file, which is called as the SRAM object file, which is a .so file that is available, and what is the device also you could able to see that. And it is asking here, do I need to program it? You could able to see that yes, it is program configure. It is ready right now. Now I have connected the USB blaster, which is USB 0, that is connected to it, and then I'm going to program through JTAG. Right, I could say start here, then you could able to see that whether it is programmed. It shows programming failed. Again, I start here. Now it shows 100% successful. Now you could able to see that in my board, I could able to change the switches which I have configured for SW0 and SW1, and I could able to see whether that LED 0 is glowing, whether it is 1 or 0. That is possible. So we have programmed the design successfully with the traditional method, and then you could be able to see the output on the board. But what is the challenge here when you say? The challenge is, since the board is not available with us, that means we cannot connect it physically, and we wanted to access the board remotely. There are methods that could be possible for us. Okay, we will understand that how do we get that logic in detail. But before getting into that process, we need to understand that what happens in synthesis process and what happens in the filter process and what happens during the programming process. So I will spend some time in the slide and then we will enter into the logic of the remote control. So we have done this small design right now, and then we have done pin planning, and then we program the design onto the board, and then you could be able to see that what is the device that is available, and you can locate this ANDGate.sof file in the output files directory. You could be able to see here output files / it shows. Why this is important for us? Because during our remote lab also we are going to locate the same SRAM object file. Let us get into the details right now. One by one we will see. The first thing what we need to see is the flow. So now you could get an idea that why is the step and what are the steps I followed. We have developed a small Verilog code. We performed analysis and elaboration, which helped you to check the syntax, and then it performed initial synthesis for us. And then it performed the synthesis. During that, we could be able to see the post mapping, and we have seen the functional netlist, and then we performed a functional simulation using the model sim. Then the next step is called the fitter, where we are performing placement and routing, and then you generate the programming file. So the process stops here, okay? And then we program the design, and then we have seen the output onto the board. And tomorrow the focus would be on the timing analysis, where we will apply timing constraints, and then we'll check whether the design is having any setup or hold violations. So we have applied the constraints. We applied the pin constraints for the design. I showed you that what is the input and what is the output. We applied the correct value, that is the IO standard values, and the correct location, and then we could be able to program the design onto them. Right, but what are the steps happening in each and every logic that we will understand in 2-3 slides right now. The first thing is called synthesis. So it translates the HDL source file into an Atom netlist. That means it can be either Verilog or VHDL or any other. It can be system Verilog also. Our main intention is to convert that HDL, that is you are translating that HDL into an RTL schematic so that you could be able to see that. So what are the very important resources in FPGA? We call that as basic resources. You have the lookup table. In our high-end FPGAs, we have adaptive logic module. We call that as ALMs. Okay, you have the lookup tables and the ALMs, and then we have logic array blocks, those things. And then you have memory resources. Then third, we have DSP resources. Then fourth, we have clocking resources. And then fifth, we have IO resources. So any resources, right? It is what is the resource it is using that we can able to see at the end of the synthesis. So the tool is going to use the gates, that is your lookup tables, flip-flops, IOs, RAM, and DSPs, and their interconnection between them. Now, what happens in the placement and routing stage, so which is very important for us to understand, because the moment we click the compilation, it does everything for us, but we need to understand that what happens in each and every step. So what is the fitter here when you say it is the advanced place and route engine? It is a placement and routing engine which helps you to find a valid solution in a reasonable amount of time. That means it performs, it is placing the components and then performing interconnections between them. Generally, what happens during placement and routing when you say there are 4 stages it runs. Stages can be run, all run or individually. So all run means when the design is very small, it is easy for us to run everything. But when the design becomes quite complex, when the design is having issues with the placement, there is no point in running the design for routing. That means we know that the implementation will take 10 hours. And then the placement is taking 3 hours, then we don't want to, and placement fails and we are not happy with the placement. There is no point in enabling the design for routing. So in that case, we can do a snapshot, which is called as a checkpoint. We do each of running each stage and we refer to that as a checkpoint. We can take a design checkpoint in each and every stage. And then once that stage is correct, then we can proceed that to the next stages. That means we can do the previous stages must be complete before running the later stages. That means we cannot directly go and do routing. Okay, you have to perform the earlier stages and then we can go to the next stage. What is very important for us is here in the earlier stage, if the design is failing, there is no point in proceeding to the next stage. So we call that as a snapshot, as I explained to you earlier. The output of each stage is called as a database, which we call that as a design checkpoint, and that is defined as a snapshot, which is useful for our incremental compilation, because when you change sometimes in the RTL, we need to add only one line in the RTL. So if you add only one line in the RTL, then you need to again rerun the design for the entire time. So for changing one line, again you need to run for 10 hours. So those things are not required right off time, right? So there are different advanced things that are available in the tool, which will take care of the incremental compile outs. So as I explained to you earlier, there is 4 stages. You have plan, and then you do early phase, then you perform placement, then it takes all the logic elements, registers, DSPs, RAMs, as I explained to you, and then it is finalizing that. So what I recollect and let you know that there are different resources. We have to understand that there are basic resources, there are memory resources, and then there are DSP resources, there are clocking resources, and then there are IO resources also. So now you could be able to see all the things in one slide. You are performing compilation. When I click start compilation, it compiled everything. Start analysis and elaboration, it performed the checking the syntax, and then it built the hierarchy for us and performed the initial synthesis. And when I click the start analysis and synthesis, it optimizes the code. When I say start fitter, it places and routes the design and then generates the output netlist for us, where we have the assembler file, the programming file ready, which will program that. Now, if you want to do everything in a single stage, we can just click start compilation, which helps you to perform everything. All right. Now, what are the different netlist viewers I showed you? That there is an RTL viewer, number 1. There is a technology map viewer, number 2. Then we also have a state machine viewer. I will show an example of a state machine viewer that is also critically required. I will open another project for you. So I will close this counter as of now. Okay, and then we'll open another project for you. So what is the meaning of a state machine viewer? If your code is a state machine, whether it is a Mealy or Murray, okay, you could be able to see that what is the logic given by Quartus to enable the state machine. So for example, I open a project. I have a design, okay, which is an arbiter design for you. So which that design is going to provide me the state machine. So you can able to see I have clicked here rra.qpf, which is a Quartus project file. We have seen 3 viewers. Number 1, the RTL viewer. Number 2, the post mapping. And then we also seen the post routing. Now we are trying to see how we can enable the state machine viewer for this example. So I just again perform compilation for you. Okay, so this design is an arbiter design, which definitely have request and grant. Okay, so instead of directly entering into the RTL code, you can be able to see how the code is getting converted into a state machine. That's what we are trying to see here. So whatever will be the complexity of the design, the Quartus will help you out to enable the logic, and then you can see different viewers here. Okay, in the earlier discussions, we have seen 3 viewers, that is all 3 netlist viewers. But in this example, we can see the 4th one also, which is called as a state machine viewer. So it doesn't mean that for this design, we cannot enable the other 3. Yes, definitely. Other 3 also we can see. But along with that, we can also see the state machine viewer logic here. Okay, all right. You go here, tools, and then you go to netlist viewers. Then you can go to state machine viewer. So now you could be able to see here request 3. request 0, request 1, request 2. Then you have grant 0, you have grant 1, you have grant 2, you have grant 3 also. Are available. Not only that, what you can also see is the transition from the source state to destination state, and in what condition it is transiting from one state to another state. That also we can see, along with the encoding techniques, whether it is binary encoding or gray or one-hot encoding or almost one-hot, which kind of encoding techniques are used for this design could also be seen by the Quartus. This is one small example for you that when you have a complex design which can be enabled as a state machine, whether it is Melee or Moore, you could also able to see that. So I have shown all the 4 netlist weavers right now. That is, one is the RTL weaver. Then we have seen post mapping and then post fitting, that is after placement and routing. And then we have also seen the state machine weaver for this example. So I'll close this. Fine for you. Right. Now we will come back to the logic here. So what is the compilation report I showed you for a small example? It contains all the compilation processing information for you, resource usage I have shown, and what are the pinouts, and what are the settings and constraints applied, and as well as the messages. Everything we can go. You can go through each and every report and understand them one by one. For example, you can go to synthesis report, which is synthesis RPT. You can do fitting report and then planned report. Everything we can get it. And this is the snapshot which I showed you, which shows that all the flow status in detail. And then it shows the family, device, logic utilization in ALMs, because it is an area 10 device, which we call that as an ALM. Okay, and then you have total number of registers, and then DSP blocks, everything it shows. And then you can also see the resource usage specifically. Okay, it doesn't mean that you can see only in the compilation report. You can expand this here. And then you can go to the filter and then you expand to the resource section here, and then you could be able to see that resource usage summary, where you could get the resources here. What are the resources that are available that you can able to see here? Combinational logic with no register that is provided, and total number of registers it is showing 0. So these are the things that we need to be very clear with the understanding of the reports and understanding of the resource usage. And all the weavers I have shown you, RTL weaver, as well as the technology map weavers. The RTL weaver is shown to you, which is the schematic weaver. And then that RTL weaver will help you to just see the number of pins, registers, muxes, and an OR gates. It uses the technology independent schematic for you. Whereas when we enter into the technology map weaver and then after replacement and routing, you could able to see IO pins and cells in terms of logic, memory blocks, as well as the MAC unit, which is called as a multi-layer, and accumulate unit, which is a DSP block. Right. Now comes the pin planning. I shown you what are the ways to perform pin planning. You would have able to see the package view, and then I showed you what are the pin names and in what is the direction and what is the IO standard I applied and showed you. That is present in the slide for you for reference. And then we enter into the programming file. So we use SRAM object file, which is used to configure FPGAs directly from the Intel Quartus Prime software. This is the one which we use for the demo there. And then you could able to see the USB blaster. We went to tools menu, and then to the programmer, and then automatically it selected the SRAM object file from here, and then it showed the progress, and then it showed that is 100%. This is the entire flow which I showed you today to understand what are the different features that are available in the Quartus Prime design software. And we have taken a small design and then we have entered into the flow. So let us explore on how do we access these informations in the remote lab right now. For the same DE10 Lite, we will do that, and the rest of the things we can discuss that in detail later. Let us understand the need for why do we need to go to the remote console first. What is the objective we are going to see is called as the remote lab. So what is the meaning of that remote lab when we say? The idea is how are we going to access the GUI of the boards remotely? This agenda is you have to install the remote DE10 Lite or DE2115 or DE1SOC the kit scripts. You need to launch the task. We have multiple examples that are available for the remote console projects. And then you need to connect to the development kit. And then you have new remote console projects. And then we are going to host the development kit. We are going to see 3 different examples, starting from small example. And then we have a design in which we use the sequential logic, which is a clock divider, which we call that as a night rider. I will show those examples one by one. And then I will also explain the flow to set up what are the scripts and how do we need to do it appropriately. So what is the need for this specific remote lab addressing logic? In June 2020, we launched initiatives to help the remote learners. We addressed a situation where student does not have a physical board in their possession. So there are 2 different things. One is based on the simulation, which we call that as DSIM. The other one, which requires the hardware board, in which we ensure that the Quartus Prime Lite Edition software is installed in the system, in the local system. Okay. Let us start with the understanding of what is available inside the remote lab. What are the requirements I explained you? It can be a Windows machine or Ubuntu machine. Quartus Prime, and then access to local or remote development. So you have access to local, that means I'm going to just access my board locally, which I have connected to the laptop. Or when it is a remote development kit, then I need to provide the IP address and the password to access the server. Where the boards are hosted in the server, I need to access them. So what is the basic funda behind this is there is a top level module. And then you have a user-defined module in which your Verilog code is there. And then you have a pin IP module where the pins are exactly configured. And then you have a remote console GUI. So you have to do 2 steps. One is configuring this portion that is in the Quartus. The second one is you need to configure this remote console GUI for the tasks. If we enable these 2, we could be able to see how the remote lab function works right now. First, we will understand that where they are available, how we are going to access them one by one. So this is the GitHub site where you have all the hands-free examples that are available. I just click this link. So this takes to a page where you could be able to see dev kits. There are 3 dev kits which we have enabled right now. One is the DE10 Lite, which is based on the Max 10, and then DE1SOC Cyclone 5, and then DE2115 Cyclone 4. Then today we are going to use only DE10 Lite board, which is our Max 10 device, because the example what I shown is also based on the DE10 Lite. So we will try to explore the examples which is based on the DE10 Lite target board right now. So you have to link and then you entered into the dev kits here. And then here we can click DE10 Lite. Here you could able to see example projects. Number 1. Remote console DE10 Lite and the remote console DE10 Lite kit. There are 2 things. What are those things? We will understand that later. First, we will click example projects and see what are the example projects that are available here. So you could able to see there are multiple examples. We will see 3 examples right now. One is the simple OR gate, like the way how I showed an AND gate. We could able to see the how the OR gate functions, and then followed by the parity example, and then the Night Rider 7-segment example, which is very interesting for you to see how we can utilize all the switches and the LEDs as well as the hexadecimal displays, which is a clock division example for you. So what we are supposed to do is we have to see here, there is an OR gate example that is available. I click here. And now you could be able to see that it has an OR gate, which is a Quartus archive file that is available, which I need to unarchive and then use in my design. What is this design? It shows that this is a simple project. It shows the OR digital logic gate functionality. You are going to change the switch and then you are going to see the LED. So the earlier design which I have done with the hand gate, I could be able to change the switch, okay, in my laptop, but then you couldn't see that whether you are getting the correct output or not. But in this specific example, what I am going to show you is we are going to take this design and then I am going to take you through the flow where you could be able to see the GUI of the DE10 light on the screen, and you could be able to change the switches and see what is happening. Okay. Right. So to do that, what is the first step I need to do is I need to download this Quartus archive file so that I could start the project. Just click here, Quartus archive file, and then you could be able to see download. So the moment you click that, it shows that the Quartus archive project is downloaded. You need to unarchive and then start the design exactly in the similar way what we have done earlier. You have to follow the traditional method till compilation, and there is a slight change when you perform the remote lab here. Let us go back to the design Quartus here, and then we will start and understand the project right now. So I'll go back here. I will close this project, and then I go back and then open the project here. Since I have downloaded right now, in the downloads folder, you could be able to see OR gate is available here. I just click that OR gate and say open. So it is asking me that can I unarchive and then start. Okay, it is restoring. So you say just say okay. It is available for you right now. Now, what is inside the design and what is present in the pin IP module? First, we will understand that. Now, when we open the files here, you could be able to see there is a user design. User design is nothing but you have input A, input B, output Y, and we say assign Y is equal to A or B is there. Now, if you see the top module, you could be able to see, since this device is having a 50 megahertz clock, you could be able to see max 10 clock 50, and then there are 10 LEDs. You could be able to see 9 down to 0 LED R, and then there are 6 hexadecimal displays. You could be able to see that. And then there are 10 switches, which is wire 9 down to 0 SW, and then there are all these things are written for you. What you are supposed to do, you have to write your own design, and that design you have to instantiate in that module. You need not need anything other than that in this design. What we are supposed to do, we have to create our own design, and then we need to instantiate that design in the top module, connecting that. A is connected to SW of 0. That means I'm going to use SW of 0, the switch 0 for A, and switch 1 for B, and then I'm going to see whether LED or 0 is growing or not for the set of combinations, inputs what I'm passing. Right. So all other things you don't need to touch. You just archive that project and perform compilation exactly in the similar way what we have done earlier. So I need to perform compilation tasks exactly in the similar way. So you just click here, start compilation. So the moment you perform compilation, you could be able to see that the design gets compiled, but what is the fundamental difference that we will see? Okay, this I have shown a small example. The next example, what we will see, the Knight Rider example would be a different example for you, where we are going to see all the switches are used and all the LEDs are used along with the hexadecimal displays. So till here, it is exactly like the traditional method what we followed. You need to develop the Verilog code. You have to perform analysis and elaboration, check for synthesis, all those things are same. And then you generate the programming file. Okay, you could able to see that what is the name of the task and how much percentage it takes also, you could able to see that. You could able to see that there is a difference in the background when compared to the earlier stage, because there is a remote lab script which is helping you to run in the background so that you can bring the GUI on the screen. Okay, we'll understand the demo first, and then how do we set it, that we will discuss later. Okay. Right, now it shows that 100%. So what we are supposed to do is you have to perform the tasks which we are going to see the GUI on the screen. I already have that GUI and light one. So I say here launch GUI and say start. I am starting the script. What is present in the script I will show you. So it shows the board connect. We are going to enter the SRAM object file here. I told you that should be present in the output files folder. You could able to see select.sof. Just click here, select.sof. It would be available inside the output files folder. You could able to see that there is a .sof file, which is the remote lab.sram object file. Just say open. The moment you given the SRAM object file, you have to click link. So if I have the IP and the password, I could provide the IP address and the password. Since I have connected the board locally, I can use the local here. So just say link here. Now you could able to see that whether it shows the system console starting. And then it shows launching the board GUI. Now you could able to see that the DE10 light board is available on the screen. And you could able to see there are 10 switches, then there are 10 LEDs, and then the 6 hexadecimal displays that are available here. So what we have programmed? We have programmed SW0 and SW1. So I could able to change the switch. You could able to see that. I change the switch here. Then you could able to see the. So since it is an OR gate, when any one of the input is 1, you could able to see the output. In the earlier case, we have done a traditional method. So there we couldn't be able to see the output because it is connected physically to my laptop. But then now you could be able to see the GUI. Okay, this is a very small example. Then we will take a medium complex example, which is a Night Rider example, which I will show you, in which it uses both the switches, then the LEDs, as well as the hexadecimal display. It's a clock divider example. So I can close this right now, right? And then I will open another project for you. Okay? What are the steps that need to be set? I will give the details later, but then you need to understand that how that could be accessed remotely. Go back here, and instead of this, you have OR gate. There are parity example, there is counter example, all those things. Now I can take the Night Rider 7-segment example for you, so that will help you to solve the process. So what is present in that design and how are we going to access it, I will show you now with an example. I will close this project. And then I'll open another project for you. Meanwhile, when the design runs, what is inside the script, I will show that to you. Now you could able to see there is a user design in which you have the clock divider. Our main intention is to convert the 50 megahertz clock into 1 hertz, so that you could able to see that what happens in the clock division in the LEDs. You could able to see the frequency in the LEDs. You can see that. Along with that, you can also view that in the hexadecimal displays. That's the main logic of this design. Let us perform compilation in the traditional way, how we were doing earlier. Once the design is getting compiled, we can go to the GitHub site again and understand that what is present inside this exam. In the dev kits, in the hands-free labs, you could able to see there is a remote console guide. In the remote console guide, you could able to see that what is available for this is for the DE2115. As I explained, we have enabled that for DE10 Lite, DE2115, as well as for DE1SoC. You could able to see that there are two steps here. One is on the script and the other one is on the Quartus. What I explained to you is on the Quartus side. To take a blank project.qar, and after taking that blank project.qar, what you are supposed to do is you take that design, you navigate through the project, take the design. This is an R-Gate example. You check whether it has been instantiated in the top module properly. You perform start, analysis, and elaborate the design. And then you launch the remote console GUI. And then you will get a window where you need to enter the username and password, that is the IP address and the password. If it is local, directly you can give the SRAM object file. And the moment you give select SOF, automatically you could able to see that board is free. So this is the step 1. So what is step 2 is how are we going to set that task, that remote console task, what is inside that we will see right now. Now, for each and every kit, you could able to see that there are 2 important folders. For example, for the DE10 Lite, you could able to see that remote console DE10 Lite.zip and remote console DE10 Lite IO.zip are 2 things. What is present inside this folder? You say the remote console DE10 Lite.zip folder has what? You say it has a set of script files. You could able to see that there is a source file which has all the tickle scripts which are available for the console, for the GUI, and for the main procedures. Similarly, there is a widget. You could be able to see, this is the widget. You could be able to see that this is for the hexadecimal displays, LEDs, and for switches, all widgets are available. And there is a script file called launch.tcl. This is what we are going to launch. So you have to download this folder and keep that in a place where you are not getting removed. It's not getting removed. It can be in a C drive or downloads folder. And then we need to configure the launch.tcl file. This is the step we need to follow. So I will explain the step right now. If you configure the launch.tcl file, and then if you can unarchive a Quartus project file and then you perform compilation and then you launch this task, automatically you could be able to access this onto the screen. Let us run, go back and see what is the process. It has done here 100%. Now, exactly in the similar way, what I do here, I try to take that. I say new IP and say start here. You could able to see that I need to give the SRAM object file. I say select SRAM object file. So it is present in the outputs folder. You could able to see that SRAM object file and say open. Then say select, right? I have done that already. And then I say link. Now it shows that the system console is getting started and then it will launch the board GUI for us. Now you could able to see the frequency of the clock. I'm just resetting the system now. How I can pass a parameter so that I can read the frequency. You could able to see that it is slowing down. You could able to see that 0, 1, 2, 4, 8, 16. You could able to see that. I am introducing another value, for example. You can able to see the frequency. Okay, right. So we have used the LEDs here, and then you could able to see the hexadecimal display so that you can able to see the division of the clock here. Clock division 1, 2, 4, 8, 16, 64, then 128. Okay. So what is another important information we can try here is this. We have seen what is happening in the clock division. If I reset the system, it is automatically getting resetted, means it is 1. If I remove the parameter from here, you could be able to see that it runs at some value. Now, instead of input from the GUI, means from here, I can do that from out the board. Means if I don't want to change anything in the GUI screen, instead I wanted to change that with output to the board, I can do that also. I remove from here and say output board means if I click the mouse here, nothing will happen. That means I cannot change any switch from here. Instead, if I change any switch from my board, which is I have connected physically, that change you could able to see that. See, I'm just trying to change my, okay, you could hear the sound that I'm changing from my board. You could able to see that it is getting changed. But then again, when I change this mode from output board input from GUI, now then I could change this. Now, the second step is known to you. What is present in the first step that I will explain to you right now. Then there are other configurations that we will discuss in detail later. Okay? What is the process here? Is you need to generate a script. We need to create a task. So how do we do that? That we will understand right now. I'll close this project. Let us open the same project which I have done RGate. Okay, I could be able to see that, and then we can compile the design. Now I'm going to create a new task for you. That means we are not going to directly take the task which I have already created. I will show you the procedure how to create your own task. That means we need to configure till the launch.tcl. What is the process that need to be enabled? We will see that. Okay, so meanwhile, let it compile. You could be able to see there are multiple examples that are available. This remote console DE10 Lite will have the basic feature where you cannot give output to board. You cannot change the board settings, your physical board, and that impact may not happen on the screen. But remote console DE10 Lite IO, you can change as well as on the screen as well as your physical. You can download any one of the scripts from here, the zip file, which has all the scripts. What I'm going to show you right now is the demo of how do we source that launch.tcl to the script. And as I explained to you earlier, there is a specific README file for you, which helps explain all the steps here. The step what is explained here, that's what I'm going to show you right now. Right, this is the remote console dev kit name. Dev kit name is nothing but whether it is DE10 Lite or DE2115, or it can be a DE1SOC.zip. Okay, and whatever steps that is shown here, that is the demo I'm going to provide it here right now for you. So that when you are free, you can go through these steps properly, and then you can host the remote console GUI. As I explained earlier, it is enabled for all the 3 boards. Okay, you can practice. There are multiple examples given for different boards. Okay, that you can practice. So it is 100% right now. I need to create a new task. Okay, you could be able to see there are 3 bars here. Just click here and say customize. After that, you could say in the existing flows, say new, and you say custom flow name. Any name you can provide here. The custom flow, for example, I say D10, I say new, and that is just FDP, something you give. Then I say OK, and you have to select tickle scripts here. So click the tickle scripts, and what is the name of the task you should provide here, and where the tickle script is located till the launch.tcl, you have to extend the path here. So the task name can provide anything. For example, I say here D10, and then say launch, I say task, some name I am providing for reference. Okay. Now, where is it is located? I double click here and go to the desktop. Then in the desktop, I have a remote console. Inside that, I have to go to launch.tcl and then say open. Okay. And then you should click OK here. Listen carefully. Here they have given the name and then I have given the paths. Just say OK, OK, and then you give OK here. Automatically, you could be able to see here DE10 light launch task and the DE10 new FTP. So the name and the script launch is automatic. This is the process I have followed. And that is the way I have showed you the OR gate example and the Night Rider example for you, which is a sequence of lights, which we have seen. The main intention, what we need to understand is how do we perform the clock division. That is very important for us. How do we convert that 50 megahertz into 1 hertz so that you could be able to see the sequence of LEDs. So just understand that information, and then I showed you the link, and now you could be able to see you have created a custom task, and then you right click task and select start. Automatically the login page will appear. The moment you get a login page, you have to, if it is connected locally, you can use local, and then the moment you give programming device and programming successful, system console will start. What is another add-on information we have is, it is not only the same OR gate parity example and Night Rider example you are going to practice. You can create your own project because you are going to download the project blank project.qar, and that will help you to create your own project. That means that is available here. You can create your own project. That means you can use it for any design. So when you take here blank project, so the blank project can be useful for any design. Wanted to create for a machine or a melee machine or a Boolean machine, for a memory or for a processor, you can download the blank project and practice. This blank project is without that IO feature. That means you don't want to change anything in the physical board, then this is fine. Now I will change something in the physical board, and that impact also I should see when you say, then you can select. So these are the different steps which I have explained you. Either you could be able to see, we have the GitHub site which I showed you, and then you could be able to see, to have the Intel Quartus Prime software posted on the student PC and the Intel Quartus Prime software hosted on the server. So you could be able to see that there are different USB hubs where you can connect, and then you could be able to access them. So we have the guide which I showed you. This guide will help you how to set up and access the board remotely. I walked through the remote console guide as of now, but then you can get more information in that. Okay. And the Night Rider lab which I showed you, which is a sequential logic, which is a clock divider example, which we have seen for practice. If you have any other questions, please let me know. Sorry, I have taken some few minutes extra. Am I audible?
Yes, yes, you are audible.
Okay.
So, are we done with the session?
Yeah, yes, I have done with the session. If there are any other questions, yes, I can.
Yeah, there are certain questions in the Q&A, if you could see.
Yeah, sure.
Yeah. Any, some questions, like a lot of questions are there.
Okay.
If we can answer some of them, then maybe some other will take in some other session.
Yeah, sure, I can do that. Not a big deal. Yeah. Q&A won't be enabled directly here.
Yeah, if you want, I can speak out the questions for you.
Yeah, please. Yeah, please.
Yeah, okay. So, just a second. In what case we need to put IP address?
Okay. So the IP address is required when you are hosting that on the server, as I showed you, right? So you are hosting your server. Then in that case, the students need to provide the IP address and the password. If they have the board that is directly connected to that laptop, which is locally connected, like what I am showing demo right now, in that case, it is not required. Is that fine? Both models are explained. You could able to see that in the guide what we are going to provide demo.
Yeah, okay. Another question is, any special considerations for interfacing the analog signal to ADC?
So there are boards with analog to digital converter ADCs and DACs available. For example, you have the Stratix 10 as well as you have ARIA 10, which are available with the add-on cards with the ADC interface is available. With that, we can definitely do that. No other special considerations are required. You have the daughter cards along with the FPGA development board.
Yeah, okay. So just a small doubt from someone, is Verilog a prerequisite for this training?
Yeah, Verilog is a prerequisite for this training. It doesn't mean that only Verilog. It can be any HDL. Either it is Verilog or VHDL or system Verilog. If you are familiar with any one HDL, it would be sufficient, because the design what we are going to do will have, for example, even if you open an example project, the project will be having some blocks which is written in either VHDL or Verilog. If you are familiar with that, it is easy for you to understand, and then, for example, you can follow different recommendations in the code, and how do we apply those recommendations. Those informations would be known to you. You can also understand what happens in synthesis and what happens in implementation when the same code is taken to the next stage, what happens like that. Otherwise, if you are not aware of the code, it is like just only the tool flow. You may not get the feature in detail.
Yeah, okay. Somebody has asked, is voltage level shifting required?
For the corresponding device, right? It is recommended to provide the corresponding voltage what is specified. Okay.
Yeah, okay. Somebody is asking, for the upcoming sessions, will we have access to remote boards to run designs?
So that's what I told you. There are different methods, right? So if you need to host the boards on the server, okay, in the institution, there are different methods that are available. We will provide you those instructions. Definitely, if you host it, then you can have a remote access. But for one or two things, we will show you how that remotely it is accessed. For tomorrow also, there is one quick session which I will show demo on that.
So I guess we are done with the Q&A. I think with this, we come to the end of our day one sessions. Yes, everyone, please keep checking the drive for updates and course materials. Thank you, Padmanabhan sir, for your wonderful talk. I hope participants might have found it very interesting and beneficial for them. So everyone, see you tomorrow. Yeah, the session starts at 9:30. So please try joining by 9:25 so that we can start the session on time. Thank you, everyone. So see you tomorrow. Thank you, sir. Thank you.
Thank you all. Thank you. Good luck. All the best.
Thank you, sir.